Hey guys, welcome back to the channel. Whether you're here to learn something new or just let your mind wander while your body rests, tonight's journey is designed to do both. So get comfortable under the covers, in your chair, eyes closed or drifting, because the story we're about to tell lives inside you. Literally. Now before we begin, if you enjoy slow science like this, a like or subscribe helps us keep making these quiet explorations. And while you're here, drop a comment below. Where are you watching from? And what time is it where you are right now? Midnight in Manila? 3 a.m. in Toronto? I love seeing which corners of the world this sleepy science finds. One small thing, even though we'll be talking about health, cells and the molecules that build us, this video isn't meant to replace medical advice, just calm curiosity and maybe a little wonder. So now, close your eyes, if they're not already. Let your breathing slow. Let your thoughts stretch out, like molecules untangling in warm water, because tonight, we're unraveling something deep, a twist that lives inside your cells, a pattern that makes your heart beat, your fingers curl, your memories stick. It's called DNA. It's been telling your story since before you were born. But here's the question that keeps scientists up at night. Did DNA really begin here, on Earth, or did it come from somewhere else? You don't need to answer right now. You don't need to do anything at all. Just drift with the question and let your body rest while your mind slowly spirals into the mystery. Let's begin. Inside every one of your cells, tucked neatly within the soft walls of your nucleus, is a ladder, but not one you can climb, not one you can even see. It's curled, twisted, hidden like a secret. And yet it holds everything. The blueprint of your eyes, the chemistry of your sleep, the recipe for how you heal. DNA, deoxyribon, nucleic acid, the long, winding molecule that writes you into being. It doesn't shout its presence, it works in silence. A spiral staircase of molecules folding inward, coiling tightly into the language of life. With just 4 letters, A, T, C, and G, it speaks a vocabulary older than cities, older than memory, older than Earth perhaps. For most of human history we didn't know it was there. We saw only the visible hair, skin, bone. We passed down stories from parent to child, and noticed how noses and tempers seemed to follow bloodlines. But the script, the mechanism, the code, that stayed hidden, buried inside us all, until 1953, when the shape finally revealed itself, a double helix. 2 strands twisted around each other in a precise embrace, like ribbon candy, or braided rope, or the threads of a very old book. But here's the strange thing. When scientists looked closer, what they saw wasn't random. It was mathematical, symmetrical, elegant. Base pairs lining up with perfect loyalty, adenine with thymine, cytosine with guanine, like dance partners in an eternal waltz. No straying, no improvisation, just order, repeated billions of times. And in that order, information, the instructions to make lungs, to knit bone, to learn a language, to fall in love. But here's what keeps whispering in the corners of the lab. Why is it so perfect? Why does DNA feel less like an accident, and more like architecture? Could a molecule this efficient have written itself? Some say yes. They point at Earth's early oceans, rich in iron, carbon, lightning, a primordial soup, bubbling with possibility. They imagine chains of molecules forming, breaking, rejoining, until one day one chain happened to copy itself. A miracle born from randomness. Others aren't so sure, because randomness, given 1 billion years, still doesn't often yield precision. And DNA is precise, self-replicating, error-correcting. A molecule that remembers, and sometimes forgets just enough to evolve. Some scientists ask, what if the ingredients didn't come from here at all? What if, long before Earth was Earth, the seeds were already drifting, encased in comets, frozen into meteorites, waiting to crash down onto warm rock and shallow sea? Panspermia, they call it. The theory that life didn't begin here, but arrived. Not aliens in ships, but molecules in motion. The soft arrival of chemistry across space, riding stardust, sailing radiation, carried by time. It sounds strange until you realize we've already found the clues. In the Murchison meteorite which landed in Australia in 1969, scientists found over 70 amino acids, some of them rare, even on Earth. They weren't made in a lab. They came from space, older than our planet, preserved in cosmic time capsules. They also found sugars, simple ones but essential, building blocks of RNA, the close cousin of DNA. And so we begin to wonder, if the parts can arrive from elsewhere, could the whole? And if DNA didn't form on Earth, where did it start? A dust cloud? An ancient nebula? The oceans of a dead moon? We don't know. But the more we look, the more likely it seems that life is portable. That the story written in your cells may have chapters that begin in places we've never seen. The double helix isn't just a shape, it's a question. It's a spiral with a past. And it might be a visitor. Inside you right now are molecules shaped by the universe, written in stardust, edited by time, carried by light. And if that sounds poetic, it's because it is. Science, at its quietest, is often indistinguishable from wonder. So, let that spiral rest in your mind, gently turning as you drift deeper. Because whether DNA began here or not, the truth is this: it is here now, inside you, unfolding, and the question remains, not just where did it come from, but who else, out there, is made of it too. It's one thing to say that DNA is a code, a sequence of letters, a long ladder wound into a spiral. But what does it do? How does it move from molecule to life? To understand, you need to look closer, not just at the twist of the double helix, but at what it holds. DNA is not a passive string, it's an instruction manual. A set of commands that don't shout, they whisper, quietly guiding every cell, every process, every second of your body's existence. It doesn't make things directly. Instead, it tells your cell what to make, what proteins to build, how much and when, like a composer writing a symphony they'll never hear. DNA passes its melodies on to molecules that can play them. Within that spiral are genes, tens of thousands of them, each one a paragraph in your biological novel. Some are short, no more than a sentence. Others stretch across pages, and together, they write the blueprint for everything you are. From the curve of your fingers, to how your brain releases serotonin when you laugh. From your resistance to certain viruses, to your body's ability to metabolize ginger. It's all there, folded in silence, waiting for the right moment to be read. But DNA doesn't do this alone. Like a master architect, it sketches the plan, then hands it off. The real builders are proteins, and to make proteins, DNA first creates a copy of the instruction, a temporary version written in RNA. RNA is faster, more flexible. It leaves the nucleus and goes out into the body of the cell, where ribosomes wait patiently, like factories in miniature. There, the instructions are read. Every 3 letters of RNA, called a codon, correspond to one amino acid. And as the code is read, amino acids are strung together, like beads on a necklace, forming proteins. These proteins then go on to do everything. They digest food, they repair wounds, they transmit thoughts, they form hair, nails, and neurons. They are the workers of life, and DNA is the foreman in the background, issuing quiet, perfect instructions. But there's something else hidden in that spiral, a memory, a history. Because your DNA didn't begin with you. It began long, long ago, passed down, copied, edited from mother to child, father to son, all the way back to the very first life form. You carry in your code echoes of ancient seas, survivals from ice ages, footprints of migrations your ancestors never wrote down. Even now, scientists find traces of Neanderthal DNA in many people alive today, ghosts of an ancient species, still flickering in the blueprint. DNA is not just personal, it's communal, shared. About 99.9% of your DNA is identical to every other human's. It's the 0.1% where your uniqueness lives, your freckles, your allergies, your laugh. And that 0.1% is everything. Even more astonishing, you share about 98% of your DNA with a chimpanzee, about 85% with a mouse, about 60% with a fruit fly, and around 40% with a cabbage. That's not an error. That's the echo of common origins. Because DNA doesn't reinvent itself for every species. It adapts, it tweaks, it builds on what came before. It is efficient, elegant, relentless, and maybe universal, because if life exists elsewhere in the universe, on a moon orbiting a gas giant, on a planet beneath twin suns, or in the ice crust of a frozen world, it's not impossible that its code, its blueprint, could look familiar. Scientists call it convergence, the idea that life, given the same laws of chemistry and physics, might evolve similar solutions even in distant corners of the cosmos. So if somewhere, on a planet we've never seen, there is a creature that lives and breathes, perhaps it too carries something spiral-shaped within, not identical, but close enough to rhyme. And maybe, just maybe, our DNA and theirs share a root system. Cosmic, ancient, invisible. It makes you wonder, doesn't it? Whether DNA is just the code for life on Earth, or a pattern written into the universe itself, a blueprint not just for biology, but for existence. If that's true, then looking inward, into our own spiral staircase, may be the same as looking outward, into the deep unknown. So rest now, let your thoughts slow, because inside your own body, the story continues. Proteins folding, enzymes building, cells dividing, life repeating, quietly, perfectly, faithfully following the blueprint you didn't ask for, but carry anyway. And perhaps, in the quiet hum of your cells, you're hearing something more than biology. You're hearing a story written by time, by stars, by something older than Earth. And that question lingers, just softly enough to follow you into sleep. Did this blueprint begin here? Or did it drift down, light as ash, from somewhere far beyond? Before there were blueprints, before there were genes, before the first strand of DNA ever curled into its double spiral, there were molecules, tiny, blind, unfeeling, but somehow already leaning toward life. To understand where DNA might have come from, we must go further back, not to ancient Earth, but to the time before Earth had a name, before continents, before oceans, when the planet was nothing more than heat, rock and storm. Earth's early environment was violent. Volcanoes belched ash into an atmosphere without oxygen. Lightning cracked across a sky thick with methane and ammonia. No trees, no rivers, no lungs to breathe. Just chemistry, waiting. And somehow, that chemistry turned into memory, because the molecules that make up DNA, the bases, the sugars, the phosphate backbone, they didn't appear by magic. They formed, they assembled, one bond at a time. The question is how. Some say it began in shallow pools, tiny tide pools warmed by sunlight, enriched by minerals from volcanic vents. They call it primordial soup, a warm, wet cradle where carbon-based molecules collided again and again, until something new happened. Replication. Others look to deep-sea vents, those cracks in the ocean floor where heat seeps up from the Earth's mantle. There, mineral-rich water spews into the icy ocean, creating a chemical gradient, a difference in energy that could drive reactions. No sunlight needed, just heat and time. In both stories, the same ingredients appear: carbon, nitrogen, hydrogen, oxygen. Simple atoms, abundant in the universe, bonding into more complex forms. Amino acids, fatty acids, nucleotides, the very letters of DNA and RNA. We've seen it happen in labs. Scientists recreate early Earth conditions, glass flasks filled with gases, electrodes simulating lightning, and sure enough, after just a few days, amino acids appear. But even so, creating a few building blocks is one thing. Assembling them into a system that copies itself, that stores information, that evolves, that's the leap no experiment has yet fully bridged. The components, the A, T, C, and G, they're just molecules. To become DNA, they need to form long chains. They need to arrange in specific sequences. They need to be stable enough to last, but flexible enough to change. How did that happen? Some researchers believe life may not have started with DNA at all. Instead, they point to RNA, a similar molecule, capable of both storing information and catalyzing reactions. The RNA world hypothesis suggests that before DNA, there was a world where RNA did everything: coding, catalyzing, replicating. And later, perhaps billions of years later, DNA emerged as a more stable long-term storage format, like moving files from a scratch pad to a hard drive, like refining a sketch into a blueprint. Still, there's a problem. Even RNA is complex, and we've never seen it arise spontaneously outside of life, which leads to a more radical possibility. Maybe the molecules didn't form here at all. Maybe they were delivered. Comets, meteorites, asteroids streaking through the solar system carrying cargo not of gold or ice, but of chemistry. Space isn't empty. It's full of organic compounds floating between the stars, hiding inside carbon-rich dust grains, coated in ice and radiation. We've detected amino acids in meteorites, simple sugars, even purines, the A and G in your DNA. Not made by life, made in space. Imagine that, a rock hurtling through the void, spinning for millions of years, crashes into Earth, and brings with it the letters. Not life, not consciousness, just the raw syllables of biology, waiting for a home. This is the essence of panspermia, not that aliens seeded the Earth, but that chemistry did. That the molecules themselves are wanderers, that life's ingredients are not rare at all, but everywhere, written into the very dust between stars. It's not as far-fetched as it sounds. When NASA sent the Stardust spacecraft to collect particles from a comet, they found glycine, a simple amino acid. We found nucleobases in meteorites, sugars in interstellar ices, carbon chains drifting through nebula. And always the question, if the ingredients are this common, how rare can the recipe really be? Maybe the Earth was not a miracle, but a moment, a place where the conditions were just right, long enough, warm enough, stable enough, for those drifting molecules to assemble, to arrange, to remember. Perhaps it wasn't the Earth that created life, but life that found the Earth suitable. A fertile pause in the wild rush of time. And if that's true, then DNA isn't just an Earth molecule. It's a cosmic one. It means the code in your cells might have cousins elsewhere. Different sequences, different species, but the same logic. Base pairs, replication, memory. So when you close your eyes tonight and feel the slow rhythm of your breathing, remember, the atoms in your chest may have once drifted through interstellar clouds. The molecules in your blood may have been frozen in a comet. The letters that write your name may have fallen from space. And DNA, this quiet, perfect script, may be far older than Earth itself. So the question deepens, if the molecules came from elsewhere, what else might be out there that carries the same story? Who else is written in the same alphabet? If DNA truly did arrive on Earth from beyond, tucked inside meteors, carried on comets, frozen inside dust, older than the sun, then it faced a problem almost immediately: survival. Because early Earth was not gentle. Picture a planet, still forming, its surface writhing with molten rock, its sky thick with choking gases, its seas acidic, turbulent, and raw. It was beautiful. Yes, but not in a way that welcomed life. It was beautiful in the way wild storms are beautiful, in the way destruction makes way for creation. And into this chaos, a fragile cargo may have fallen. Molecules, simple ones, but with astonishing potential. Adenine, cytosine, fragments of sugars. The curved backbone of a spiral not yet born. They landed hard, battered by entry, drenched by sulfur rain, bathed in ultraviolet radiation from a young and unforgiving sun. There are so many ways to destroy a molecule, so many ways it could have failed to begin. Heat, acid, time, and yet, somehow, the chain held. How? That's the mystery. How did something as delicate as a self-replicating molecule survive long enough to begin? Some scientists believe in shelter, not caves or shadows, but minerals. crystals, layered like sheets of mica, clays with microscopic crevices, tiny protected spaces where chaos softened, and delicate bonds could form without being torn apart. These mineral surfaces may have acted like scaffolding, holding molecules close, helping them align, encouraging the first connections between sugar, phosphate, and base. It's like trying to build a house during a hurricane, unless you have a quiet cellar where the wind can't reach. Other researchers look beneath the ocean, to hydrothermal vents, where mineral-rich water burst from the Earth's crust in endless scalding columns. These vents offer something else: energy gradients, where hot meets cold, where alkaline water meets acidic sea. You get natural batteries environments that drive chemical reactions without needing fire or sunlight. Inside the chimneys that form around these vents, scientists found hollow structures made of iron and sulfur, perfect little pockets, tiny test tubes, places where early chemistry might have taken its first breath. But even in shelter, replication is no small feat. To replicate, a molecule must do three things: store information, copy itself, and change, but not too much. If it never changes, it can't evolve. If it changes too much, it falls apart. That balance between stability and variation is what makes DNA so astonishing. It holds fast to the blueprint, but allows just enough flexibility for the blueprint to adapt. Imagine a book that rewrites itself, one letter at a time, very slowly, and only when needed. That's DNA. It doesn't just endure, it responds. But at the beginning, it didn't look like it does now. The first genetic systems may have been messier, shorter, simpler, chains of RNA perhaps too fragile to last on their own. But slowly, as time wore on, they found help. Lipid bubbles, primitive cell walls, may have wrapped themselves around strands of replicating molecules. By accident, a chain of RNA might have floated into one of these bubbles and discovered, suddenly, protection. And once enclosed, everything changed. Inside that bubble, chemical reactions could happen in peace. Strands could copy, mutate, compete. That competition was key, because not all sequences are equal. Some fold better, some last longer, some make more efficient copies. Over time, the ones that replicated faster and survived longer outpaced the rest. Natural selection on the tiniest scale. Not creatures fighting for food, but molecules competing for chemical space. And from that microscopic rivalry, something amazing emerged. Inheritance, a system that could copy itself with enough fidelity to stay the same, and enough error to change. That's when evolution began. Not in bodies, not in brains, but in molecules. From simplicity came pattern. From pattern came memory. And from memory came the first true replicators. Still, it wasn't easy. Even with shelter, even with competition, the early Earth was unpredictable. Meteor impacts boiled oceans, volcanoes darkened skies, lightning struck without warning. Extinctions began before species existed. But the molecules endure because once replication begins, once memory takes hold, life becomes hard to stop. A storm can kill an organism, but not a pattern. As long as just one sequence survives, it can start again. Rewrite the code. Try once more, and that's what life did. Again and again. Quietly, persistently, until patterns became strands. Strands became systems. And systems became cells. Not perfect, not conscious, but alive. We call that moment abiogenesis. The emergence of life from non-life. Not a spark, but a slow simmer. And even now, no one knows exactly how it happened. We have models, theories, experiments that get close, but we've never made life in a lab. Not truly. Because life isn't just molecules, it's a balance, a rhythm, a recursive song that sustains itself over time. And DNA, whether born in a tide pool or seeded from space, became its memory. The spiral that whispers through every cell, continue. It doesn't know why. It doesn't need to. It simply does what it was shaped to do. Store the past, copy the present, allow for the future. And so here we are, billions of years later, reading back through the spiral, wondering not just where it's going, but where it began. We still ask, was the Earth a cradle or a waypoint? Did life arise because of this planet, or in spite of it? Were the molecules native or travelers? Did they form in our oceans, or arrive folded into a meteor that burned its way through the sky and cracked open on ancient rock, spilling the alphabet across the sand? We may never know, but we do know this: it was fragile, and it survived. That alone makes everything that followed feel like a miracle. So sleep now, and let that thought stay with you, that the same molecules that now whisper in your blood once endured a world on fire, and didn't just hold on, they learned to remember. If life began on Earth, then it began spontaneously. No planning, no witness, just matter, heat and time colliding in the dark. Until one day, something happened. Something that copied itself, something that remembered. But how? How did simple molecules scattered like letters across a page arrange themselves into a sentence? This is the central mystery of biology, the leap from chemistry to life. We can explain what happens after. Once DNA exists, we know how it replicates, how it mutates, how it builds complexity over generations. But before that, before the spiral, before replication, that's where the puzzle lies. Because when we look at DNA, its structure, its precision, its ability to store information across time, it doesn't look like an accident. It looks engineered, not by hands or minds, but by necessity, by a logic that lies hidden within the laws of the universe. And yet, according to everything we understand, it had to come from somewhere. No life, then life. It seems too neat. Many have tried to recreate it in the lab, to simulate the spark. The Miller experiment in 1952 was one of the first. They sealed gases meant to mimic early Earth's atmosphere. Methane, ammonia, hydrogen, water vapor into a glass flask. Then they added sparks of electricity, simulating lightning. After just 1 week, they found amino acids, organic molecules, the building blocks of life. But no cells, no replication, no memory. Just bricks, no blueprint. Later experiments added more elements, different gases, UV light, minerals, metals, freeze-thaw cycles. Always, the result was the same. Ingredients, but never the recipe. The gap between chemistry and biology remains vast. It's like assembling every part of a watch and waiting for it to tick. That leap from molecule to memory, from accident to evolution, is where the thread frays. We call it abiogenesis, but naming a thing doesn't make it understood. Some scientists believe the solution lies in networks, not in a single molecule, but in systems. Feedback loops, chemical webs that reinforce themselves, where products become catalysts, where cycles begin to sustain and amplify. In these networks, errors become innovations. Stability emerges, and slowly, order rises from the chaos. Others point to energy. Life, at its core, is an energy transaction. It takes in fuel, does work, and expels waste. Even the earliest life must have followed this pattern. So maybe the first step wasn't replication, but metabolism, a system that processed energy first, and only later learned to remember. Metabolism first theories suggest that simple cycles of chemical reactions may have become stable, feeding off gradients near hydrothermal vents. Only after establishing reliable energy flow could a system evolve memory, RNA, then DNA, and pass it on. Still others suggest that order is inevitable, that the laws of thermodynamics, the geometry of molecules, and the sheer number of chemical interactions make life's emergence not just possible, but likely. Given enough time, enough surface area, enough shaking and sunlight and temperature change, life becomes statistically probable. But even probability struggles against complexity, because DNA is not just a molecule, it's a system. It encodes, it repairs, it regulates, it interacts with proteins, uses RNA, and depends on enzymes to do almost everything. So what came first? The DNA that needs proteins to replicate, or the proteins that need DNA to be built? It's a loop, a paradox. And yet here we are, built by that loop, sustained by it, dreaming through it. That circular dependency has led some to propose simpler systems, molecules that could do both jobs at once. RNA is one candidate, capable of storing information, but also of catalyzing reactions. In rare cases, RNA can fold itself into structures that act like primitive enzymes. We call these ribozymes, molecules that both carry a message and perform a task. A kind of molecular multi-tool, but RNA is fragile. Short-lived, susceptible to breakdown. Could it have lasted long enough to evolve? Could it have copied itself in a world without enzymes? Could it have survived without a membrane, without repair, without help? We don't know. And that uncertainty has opened the door to more radical ideas. Some suggest that life didn't begin in water at all, but on ice, where molecules could concentrate, avoid degradation, and be slowly shaped by cycles of freeze and thaw. Others look to space, not just for the molecules, but for the process itself. Could early life have begun on another planet? A moon of Jupiter? A warm pocket on Mars, long before Earth settled down? Could it have arrived fully formed, frozen in rock, only to atone here? Panspermia again, but deeper. Not just the delivery of ingredients, but of life itself. Still others float theories of quantum coherence, information encoded in waveforms, life not as chemistry alone, but as information, preserved and shared across time and space. These are bold ideas, unproven, unlikely perhaps, but they remind us how strange it is that life exists at all. That molecules not only joined, but remembered. That replication began, and with it, selection, evolution, consciousness, curiosity, you. And so the puzzle remains, sitting quietly at the edge of what we know, inviting questions, but offering no certain answers. Was it warm pools, struck by lightning? Minerals guiding molecules into place? A comet's chemistry buried in ice? Or something else entirely? A process we've yet to imagine. We may never know exactly how life began, but the wonder lies not in the answer, but in the asking. And tonight, as you lie still, breathing slowly, you are living proof that the puzzle solved itself, at least once. You are the evidence that molecules can dream, that chemistry can lead to questions, that atoms, given time, will organize into thoughts that ask where they came from. So sleep now, and let the mystery sit beside you, not as a problem to solve, but as a reminder that you are part of something vast, something still unfolding. The puzzle may be unsolved, but you, right now, are its most astonishing clue. When you hold your breath in the stillness of night, you are surrounded by life. Invisible bacteria drift on dust motes. Spores rest in dry cracks of stone. Pollen, seeds, skin cells all waiting to move, to find a place to land, and begin again. Life travels. Even here, even now. So, what if it has always done so? Not just across rivers or mountain ranges, but across space. That's the heart of a theory once whispered on the fringes of science, now spoken more confidently with every new discovery. Panspermia, the idea that life or the precursors of life did not originate on Earth, but arrived. Not in spaceships, but in silence. Not as alien civilizations, but as dust. Simple, tiny, seed-like, carried across the stars, patient as time. The word comes from the Greek pan, meaning all, and sperma, meaning seed. And that's exactly what it proposes. That life, or at least the seeds of life, are scattered throughout the cosmos. Waiting, drifting, falling like rain on young planets, with oceans warm enough to receive them. At first, it sounds too poetic, too science fiction, but the pieces, the chemistry, the physics, the evidence, are starting to align. Because space is not empty. It's full of organic molecules. Simple amino acids have been detected in meteorites, Sugars frozen in comet ice, carbon chains drifting in the dust between stars. And not just a few. In the Murchison meteorite that landed in Australia in 1969, scientists found over 70 different amino acids. Only a handful of those are used in life on Earth. The rest? Unknown, but clearly organic, and older than Earth itself, formed not in oceans but in space. There's a comet called 67P, a frozen dusty rock orbiting the Sun. The Rosetta spacecraft landed on it, and what it found stunned everyone. Glycine, the simplest amino acid, and phosphorus, a key component of DNA. All drifting through deep space, on a rock older than your planet. Even more astonishing, we've learned that some organisms from Earth can survive in space. Tardigrades, the microscopic water bears, have survived the vacuum of space, radiation, and extreme temperatures. Brought to low orbit, exposed directly, they came back still alive. Even certain spores, bacterial, fungal, have endured in Earth's upper atmosphere, and some scientists suspect they may even arrive here, falling from above, riding air currents that stretch beyond our clouds. Life wants to spread. And that makes panspermia more than a theory. It makes it a possibility. A quiet one, but profound. It doesn't require alien intelligence. It doesn't even require DNA. All it needs is a rock, a molecule, a bit of luck, a meteor blasted off a planet by an impact, encased in ice, or dust, or carbon, drifting for 1,000,000 years, then falling into the sea of some younger, quieter world, Earth. For example, if just one self-replicating molecule survived the journey, or even a strand of RNA, half-formed waiting to be finished, then Earth may not be the birthplace of life. It may be adopted. Some even wonder if life started on Mars, when it was warmer, wetter. Perhaps its early oceans fostered the first strands, only to be lost as the planet dried. But not before ejecting rock, meteorites, some of which found their way here. Martian meteorites have been found on Earth. We know the exchange is possible, so the timeline is not impossible. In this version of the story, we are Martian orphans, raised by Earth, coded by dust from a world now silent. And that dust, those molecules may have come from even farther back, because the chemistry of life is not Earth's alone. The carbon, nitrogen, oxygen, they are born in stars, in the violent deaths of suns, in the hearts of novas and supernovas, where simple atoms fuse into complex ones. You are, quite literally, made of star stuff. That part we've known for decades. But what if the arrangement of those atoms, the specific sequences that create replication, memory, meaning, are also ancient? What if the universe has always been coding, and DNA is simply one version of that code? Panspermia doesn't say all life began the same way. It doesn't deny Earth's creativity. It simply expands the origin story. Instead of one world, we get many. Instead of one spark, we get embers, traveling, colliding, lighting fires where they can. A slow, quiet migration of molecules. And what if it's still happening? What if seeds are still falling, invisible, rare, but real, carrying codes we haven't seen, arrangements we haven't imagined? Could a strand of RNA, falling onto Europa, begin again? Could Titan, rich in hydrocarbons, be stirring its own recipe? Could there be cousins to DNA, not identical, but parallel? Chains of different sugars, different bases, but the same ambition to copy, to remember, to persist. It's not a question of belief, it's a question of odds. And in a universe with trillions of planets and billions of years, it's hard to argue that Earth was the only landing site. So rest now, and imagine this: a dust grain, spinning slowly through interstellar space, frozen, ancient, carrying within it the 4 letters of your alphabet, A, T, C, G, and after 1,000,000,000 years of drifting, it falls onto a warm young world, just calm enough to listen, and begins again. Life, not born, but delivered. And you, a page in a story that began light years away. Out beyond the atmosphere, beyond the comfort of blue skies and filtered sunlight, rocks are always falling. Cold, silent, some no bigger than a grain of rice, others large enough to scar a continent. They do not fall often, but when they do, they bring stories. Not words or symbols, but molecules frozen in time, carved in the chemistry of places Earth has never seen. They are called meteorites, fragments of ancient collisions, remnants of the early solar system, of planetary bodies that never finished forming, or were shattered long ago. When one lands here intact, untouched by human hands, it becomes a kind of time capsule, a message in mineral, waiting to be read. And when we read them, we find life's handwriting. Not life itself, no fossils, no cells, but the building blocks. Amino acids, sugars, bases that look suspiciously like the A, T, C, and G curled inside your DNA. And they are not terrestrial. They were not made by bacteria, they were not contaminated in flight. They were formed elsewhere. Take the Murchison meteorite. It fell in Australia in 1969. Locals smelled it before they saw it. A strange scent, earthy and sweet, like tar and almonds. It broke apart upon landing, and when scientists studied its pieces, they found something remarkable. Over 70 different amino acids, many of them unknown to life on Earth. They also found purines, the same ringed molecules that make up half of DNA and RNA. These weren't modern contaminants. They bore the unique isotope signatures of space. It was as if the meteor had carried a molecular alphabet, not a full sentence, but all the letters needed to write one. And that meteor is not alone. The Tagish Lake meteorite in Canada, the Orgueil meteorite in France, the Avuna meteorite in Tanzania. Each tells a similar story, carbon-rich material, frozen for billions of years, containing compounds that resemble life's ingredients, not just amino acids, but aldehydes, ketones, hydrocarbons, all woven into the rock, like dried ink in a scroll. Even ribose, a sugar essential to RNA, has been detected in meteorites. Delicate, easily destroyed, yet somehow preserved for longer than Earth has existed. It raises a profound question. If these molecules form so easily in space, what does that say about the universe? Perhaps chemistry leans toward life. Perhaps the laws that shape atoms also shape meaning. Perhaps the code in your cells is not a rare accident, but a common tendency, a direction built into the fabric of matter. In 2020, scientists announced something even stranger. Meteorites found in Antarctica contained nitrogen-bearing organic molecules unlike anything made on Earth. Not just variations of what we know, but entirely different chemistry, alien, but oddly familiar. It doesn't mean alien life, but it does mean alien possibility. Because if molecules like these exist on meteorites, then they existed before Earth, before oceans, before DNA. And that suggests that the chemistry of life may begin not with biology, but with physics. Atoms combine, energy flows, and slowly patterns appear. Not because they are alive, but because the universe allows them, encourages them, pushes them, molecule by molecule toward complexity, and then, eventually, toward memory. Meteorites may be silent, but they are not empty. They carry pieces of a story that didn't begin on this planet. Each one that falls brings with it a trace of deep space. Not just rock, but potential. They are chemical ambassadors from before Earth had clouds. Frozen messages from the asteroid belt. Some may even be older. Fragments of stars long gone. Solar systems that never stabilized. Worlds that tried and failed to harbor life. And still, they carry the ingredients. So imagine this, a meteor, no larger than a football, drifting for millions of years. It forms in the rubble of a dying planet. It tumbles through the cold, gathering ices, organics, minerals, and one day it strikes a blue planet with oceans. In the flash of heat as it enters the atmosphere, some of its material burns away. But deeper inside, protected, the chemistry survives. It lands, breaks open, and molecules spill into the sea. They swirl, dilute, interact. And slowly, something stirs. Not life. Not yet. But a direction. Meteorites don't deliver life. They deliver conditions. They carry what life needs, not in perfect order, but in potential. And if even one molecule finds the right pocket of warmth, the right mineral surface, the right cycle of wet and dry, it might begin again. This is the quiet message of meteorites, that life is not a miracle that happened once, but a possibility that happens often when the universe is ready. And Earth may simply have been prepared by ice and dust and rock that fell from the dark and cracked open to reveal not answers, but promises. So as you drift now, into sleep, into silence, let the thought rest with you, that you may carry in your blood a memory of something not born here, that the alphabet in your cells was first whispered by stars and delivered by stone. If life is fragile, then how does it keep surviving? Not just through time, but through fire, ice, radiation and silence. If DNA came from somewhere else, from a distant rock or frozen cloud, how did it survive the journey? To understand that, we have to look at the lives that already survived the impossible. Here, now, all around us, often too small to see. They are called extremophiles, not just organisms that tolerate harsh conditions, but organisms that thrive in them, that grow in boiling acid, in freezing salt water, in caves with no light, in radioactive ruins. They live where we cannot, where logic says they shouldn't. And yet, they persist. On the floor of the Pacific Ocean, near hydrothermal vents that belch sulfur, at temperatures over 120 degrees Celsius, there are tube worms and bacteria that flourish in total darkness. No sunlight, no oxygen, only heat, minerals, and chemistry. In Antarctica, beneath layers of ice and rock, tiny microbes live in subglacial lakes, sealed off from the surface for millions of years. In dry deserts, in alkaline lakes, even in nuclear waste, we find cells, breathing, replicating, remembering. One of the most famous extremophiles is the tardigrade, also known as the water bear. It's less than a millimeter long, with 8 stubby legs and a strange, crumpled face. But what it lacks in size, it makes up for in survival. Tardigrades can be frozen, boiled, dried out, exposed to space, and still, they live. They enter a state called cryptobiosis, a kind of molecular stasis. They shrivel, expel water, wrap themselves in sugar glass, and wait. Years later, add water, and they return, alive. Resuming their slow, quiet crawl, they have survived conditions that mimic deep space. They have been sent into orbit and returned, still breathing. How? Because life is not just delicate, it's adaptive. And extremophiles show us that biology is not limited to calm, green worlds. They are living proof that life can begin or survive in places we once thought impossible. Some bacteria resist radiation by rebuilding shattered DNA. Some archaea, single-celled and ancient, survive in acid stronger than vinegar. Others in salt lakes that would kill most fish in minutes. Their enzymes work under pressure, heat, and chemical stress. Their membranes are fortified. Their replication processes can stall and resume. They teach us that life is not just tolerant, it's clever. And if it can thrive in such places on Earth, why not beyond? Europa, one of Jupiter's moons, is covered in ice, but beneath the shell, scientists suspect a liquid ocean, dark, cold, pressurized, but possibly warm at the core, from tidal flexing or volcanic heat. Extremophiles suggest, yes, life could be there. On Enceladus, a moon of Saturn, plumes of water spray into space. In those plumes, organic compounds. Could microbes live in the cracks below, feeding off minerals as they do near Earth's vents? Mars, once wet and warm, now dry and frozen, may still hide life deep underground, where heat lingers and salt brines stay liquid. If extremophiles were born there, they might still be hiding, and if they came from somewhere else, they might never have left. Because extremophiles don't just endure, they travel. Spores, for example, tiny, lightweight, resistant to desiccation and UV radiation. They can float in the upper atmosphere, even into space, riding dust. Some scientists believe spores could survive for millions of years in the vacuum of space if protected by a thin layer of rock. It's not science fiction, it's survival science. We've recovered bacteria from inside salt crystals, 250 million years old. We found spores buried in permafrost, revived after tens of thousands of years. Life waits. Which brings us back to the question: if a meteorite carried life, or even just its instructions, through the cold dark of space, could it have survived the fall? Extremophiles suggest yes. The spore, protected inside porous rock, shielded from radiation, drifting through time, landing on a young Earth. It might awaken, stretch, divide, and begin again. And what's more, some researchers believe Earth may be sending life out even now. Every major asteroid impact launches fragments of Earth into space. Some escape orbit. Some land on the moon. A few go farther. And if any of those rocks carry bacteria, then Earth may be a seed as much as a garden. The universe may be filled with drifting spores, each one carrying the potential to write a new story in a new world. And DNA? It is the journal, the structure that records the memory, the molecule that remembers how to begin again. Extremophiles show us what DNA can endure, what it can build back, what it can survive. They are not outliers. They are hints of what life can become, of where it may have started, of where it might go. So as your body settles into the softness of sleep, let your mind drift outward, beyond Earth, beyond breath, and imagine a single cell, spinning through space, tucked in stone, curled tight against radiation, carrying a code older than rain, waiting, not for rescue, but for arrival. There's a quiet idea that lingers in the mind like mist. Not a loud theory, not a declaration, but a possibility, soft and steady as gravity. Maybe life doesn't just survive worlds. Maybe it moves between them. Imagine this. Somewhere on a young planet, Mars perhaps, long before its deserts formed, a small rock is dislodged. An asteroid strikes. The impact is violent, hot, unforgiving. Debris is hurled skyward. Some fragments rise high enough to escape gravity entirely. Not just flying, leave among them a speck of rock, no larger than a fist, riddled with tiny pores and crystal veins. Inside one of those pores, sheltered in darkness, a single cell, a spore, a passenger. It doesn't know what's happening. It doesn't need to. It's dormant, dry, frozen, and soon, spinning slowly in the vacuum, it becomes a traveler. No engine, no wings, just momentum and silence. That's the quiet heart of lithopanspermia, the idea that rocks ejected from one planet can carry life to another. It's not a theory of fantasy. It's grounded in physics. We found meteorites from Mars on Earth. Confirmed, studied, named. They bear Martian isotope signatures. They match what we've seen from rovers and orbiters. And if rocks from Mars can reach Earth, then Earth rocks can leave too. It takes time, thousands, millions of years. But it happens, and inside those rocks, if the pores are deep enough, the radiation low enough, the temperature cold enough, life may survive, shielded against cosmic rays by just a few millimeters of stone, locked in stasis, no replication, no decay, just waiting. The vacuum of space is not kind. It offers no warmth, no air, no comfort, but for certain microbes, for spores, tardigrades, and radiation-resistant bacteria, it isn't death. It's sleep. Studies have shown that bacteria encased in rock can endure deep space conditions for at least several years. Extrapolated, that endurance might stretch longer, centuries, perhaps millennia, depending on their journey. In 2020, a Japanese experiment placed bacteria outside the International Space Station for 3 full years. When the samples returned, some were still viable, still alive, still able to replicate. And that's in low Earth orbit, near the protection of our magnetic field. Imagine what a thicker rock deeper inside space might preserve. Not all would survive, but life doesn't need most. It only needs one. One surviving cell. One seed. One successful landing. And from that, a world can change. Now imagine the landing. A planet like Earth, just forming, still cooling, its surface cracked with lava, its skies thick with vapor, but already oceans. The traveling rock, dark with age, pierces the atmosphere. It heats, its surface chars, but inside, coolness remains. It crashes into the sea, sinks, breaks open, and there, at the bottom of a warm tide pool, life stirs. Not born, but arrived. Is that how Earth began? Some think yes. Some believe Mars may have been more habitable earlier, that the first replicators might have formed there. And when Mars dried, they left, not willingly, but as fragments. Others believe the journey was longer, that the building blocks came from comets, that life traveled not across a solar system, but between stars, that a solar system disrupted by its dying sun scattered debris across interstellar space. Some fragments, rich in organics, drifted for billions of years before being caught in the gravity of a new star, our Sun, and among its planets, Earth, young, blue, empty, until the rock arrived. That's interstellar panspermia, a theory still in its infancy, but not impossible, because space, for all its silence, is not empty. It is alive with movement. Comets, asteroids, planets, all in motion, all crossing paths. And while the odds of a life-bearing rock landing just right seem low, consider the scale. The universe is vast. The time is long. And life only needs a single success. This idea, that life can travel, leap, wander, reframes everything. It means biology may be interconnected, that the chemistry of one world may echo in another, that the code in your cells might not be unique to Earth. And maybe, somewhere out there, a cell has landed. Maybe it's already begun replicating. Maybe it will one day look up at unfamiliar skies and wonder, just as we do, you, lying still now, half asleep, surrounded by molecules that copy and repair and dream. You are part of that motion, a ripple in a cosmic sea that stretches beyond galaxies. You are proof that matter can become memory, that molecules can become meaning, that the universe wants to know itself. So could life travel across worlds? It already has. You are its evidence, and somewhere, another journey may be beginning. A rock, a spark, a strand of spiral code, folding softly in the dark, waiting for the right planet to open its arms. Comets, cosmic delivery systems. They come from the edges, from places so distant, so dark, that sunlight is only a rumor. They move slowly for centuries, quiet, cold, invisible, until something nudges them. A gravitational tug, a passing star, a shift in orbit, and suddenly, they begin to fall. Comets. Icy bodies older than Earth, older than the moon, older than the very oceans that would one day ripple with life. They are messengers from the outer reaches, carriers of frozen secrets, sealed away for billions of years. We used to think of them as omens, blazing trails across the sky, warnings or wonders, depending on the age you lived in. But today we know them differently, not as symbols but as capsules, cosmic delivery trucks, ferrying material across the solar system, and perhaps across time, because comets are not just ice. They are chemical treasure chests. Inside their frozen cores, water, carbon dioxide, methanol, formaldehyde, ammonia, hydrogen cyanide, and most importantly, organic molecules. On the comet 67Pa, Chimo, Gerasimenko, visited by the Rosetta spacecraft, scientists found something astonishing: glycine, an amino acid, and phosphorus, essential for DNA and cell membranes. On other comets, we've detected alcohols, simple sugars, even precursors to nucleobases. It's like the ingredients for life were packed into a frozen suitcase and sent wandering. But how do comets deliver? They begin in the Oort cloud, a vast halo of icy objects surrounding the solar system, stretching light years into space. Or in the Kuiper belt, closer in, just beyond Neptune. There, comets sleep, motionless, forgotten, until disturbed. When they fall inward, toward the sun, they begin to warm. Ice sublimates, dust lifts, and a glowing coma forms, a bright, ghostly halo. The tail stretches for millions of kilometers, a trail of particles that follows them like memory. But beneath the glow, beneath the spectacle, is a payload. Molecules forged in ancient chemistry, unexposed, unaltered, possibly unchanged since the dawn of the solar system. When a comet strikes a planet, its speed is tremendous, tens of kilometers per second. The energy released can vaporize rock, but not all of the comet burns. Some of its material, especially if buried deep in the core, survives. It mixes with the atmosphere, the oceans, the crust, and over time, it becomes part of that world. That's the theory behind delivery panspermia, the idea that comets are not just wanderers, but couriers, that they may have brought not just ingredients, but momentum. There's evidence, not just in meteorites, but in Earth's own history. In 2009, NASA's Stardust mission collected dust from the comet Wild 2. When it returned, scientists found organic compounds including glycine from a comet collected in space, confirmed on Earth. Not a guess, not a contamination, a direct delivery. And then there's the late heavy bombardment, a period about 4 billion years ago when Earth and its neighbors were pummeled by debris, comets, asteroids, countless impacts. Some scientists believe that during this chaotic era, Earth received vast amounts of water from comets, perhaps most of its water, and along with that water, organics. It's possible that life's ingredients rained down, not once, but over and over, each impact, a cosmic whisper. Here, try again. It's poetic, yes, but also practical. Because comets, unlike asteroids, are cold. Their interiors are shielded from heat. So even if their surfaces burn, the cores remain intact. If you were a fragile molecule, riding across space hoping to find a place to begin again, a comet would be your ark. Now imagine it. 1 billion years ago, Earth is young. Its oceans steam. Its skies are red with haze. The comet falls, crashes into the ocean, splashes steam and rock into the air. And from the fragments, new chemistry begins. Not life yet, but motion, interaction, possibility. And maybe, after 100 more comets, 1,000, something clicks. A strand forms. Not perfect, not stable, but almost. It copies itself. Poorly, but enough. And then, evolution begins. So if life arose quickly on Earth, as the fossil record suggests, perhaps it's because the ingredients were delivered, not slowly built, but gifted. It doesn't make life less special. It makes it shared. It means life may be woven into the structure of the solar system itself, that every icy rock, every dusty tail, may carry echoes of biology. Even today, we see it. The Oort cloud still surrounds us. The Kuiper belt still drifts. And comets still fall. Each one, a frozen message from a time before memory. Each one, a chance that somewhere, in the chemical hush that follows impact, life might rise again. As you rest now, breathing slowly, know this. You carry molecules older than Earth, atoms forged in stars, possibly delivered by comets that never burned away. You are the living answer to a question written in ice. Every story has a beginning, but sometimes the beginning is buried inside another beginning, a hidden chapter that came before the pages we know. We speak often of DNA, its double helix, its elegance, its grip on memory, but the question remains, did DNA write the first words of life, or was it simply a copyist, taking over a story already begun? There's a theory, a quiet one, but growing louder, It says DNA wasn't the first keeper of the code. It wasn't the spark. It was the library. The theory is called RNA World. And in it, life's story begins with a molecule more fragile, more reactive, but more versatile. RNA, ribonucleic acid, a cousin of DNA with a different sugar in its backbone, and a single strand instead of a double, where DNA holds the master blueprint. RNA plays many roles: messenger, translator, editor, and even enzyme. It moves, it folds, it acts. In the modern cell, RNA is a middleman. It carries instructions from DNA to the ribosome, where proteins are built. But in this theory, RNA wasn't just a courier, it was the origin. Long ago, before cells, before membranes, there may have been a world made entirely of RNA, a time when strands floated freely, copying themselves, evolving, interact, because RNA has a unique power. It can store information, like DNA, and it can catalyze reactions, like proteins. It can fold into shapes that act like primitive enzymes called ribozymes. These structures can snip other RNA, copy themselves, and perform simple functions. In a world without proteins, without DNA, RNA could have done both jobs. A one-molecule system, a self-starter, that's the idea. Experiments have shown that some ribozymes can link RNA bases together, a step towards self-replication. Others can cut and rejoin strands. Some can even evolve in the lab, under selection pressures, to improve their function. It's not life, but it's close. The challenge: RNA is delicate. It breaks down easily. It doesn't last in heat, or UV light, or acid. And yet, it still may have been enough, because early Earth had pockets of protection. Cool pools, clay minerals, frozen lakes, deep-sea vents. And in these niches, RNA could have assembled, one strand at a time, copied itself, changed, improved. Then, as the environment changed, as systems grew more complex, DNA emerged, stronger, more stable, better at long-term storage. It didn't replace RNA, it partnered with it. The two became a team: DNA to store, RNA to act, proteins to build. A three-part engine, still running in every cell today. But what if it was DNA first? Some researchers suggest that DNA, despite being more complex, could have formed directly. Under the right conditions, its nucleotides can assemble. Its double helix offers protection, built-in repair, longer memory. And in meteorites, we found deoxyribose, the sugar in DNA, not just ribose, for RNA, but its more refined sibling. It's possible that both molecules arose together. That early life tried many paths. Some used RNA, some DNA, some combinations we no longer see. And only one system proved stable enough to last. The cell, as we know it, is the result of molecular trial and error. We only see the survivors, the winners of a billion-year race. But once in those early pools and cracks and vents, RNA may have danced freely. It may have ruled. It may have been the voice of life's first sentence. Even now, it holds ancient power. The ribosome, that molecular machine that builds proteins, is made mostly of RNA. Not protein, not DNA, RNA. It folds, it acts, it remembers its old role. A relic. Still working, still essential. As you lie still now, and your cells quietly divide, remember that inside each one, this ancient rhythm plays on. DNA coils in the nucleus, silent and guarded. RNA flutters out, reads the code, carries the message. And in the cytoplasm, ribosomes built from RNA assemble the parts. It's a process older than history, older than thought, perhaps older than Earth. So did RNA come first? Was DNA a perfection of its story, or did they rise together, hand in hand, in a world that barely knew how to count time? We may never know, but in the spaces between your breath, in the pauses between heartbeats, this process continues, quiet, faithful, miraculous. And as your body rests, a question hums in your cells: which molecule dreamed first? And what did it see? It twists. Not wildly. Not chaotically. But with perfect rhythm. A spiral, gentle and sure, like a staircase spun from light. Not jagged. Not random. But balanced. Two strands, each mirroring the other. Winding upward and inward, endlessly copying themselves. This is DNA's shape, but it is also its mystery. Because the double helix isn't just beautiful, it's efficient, elegant, exact. And that leads to a quiet question, whispered in labs and lecture halls alike. Is the double helix too perfect to be chance? We know how it works. We've mapped it, modeled it, modified it. We know how the bases pair. Adenine with thymine, cytosine with guanine. We know how its structure coils, how its code is read, how it directs the symphony of the cell. But why does it look the way it does? Why a helix? Why this helix? And more importantly, why does it work so well? Because DNA is more than just a container for information. It's a solution. A molecule that stores data, replicates with fidelity, mutates with just enough error to evolve, and protects itself with symmetry. It is stable in the right ways, flexible in others. It resists damage, it allows change. Its bases ATCG form hydrogen bonds across the strands, locking them in place, but gently enough to unzip when needed. Its backbone, a sugar phosphate ladder, gives it structure and strength. Its antiparallel orientation, one strand running up, the other down, allows precise copying in opposite directions. Everything fits. And that's what makes people pause, because randomness, for all its creativity, rarely produces something so clean. Imagine writing a code with only 4 letters and building from it every whale, mushroom, hummingbird, and human. Imagine folding that code into a spiral so compact it can be tucked into the invisible heart of a cell. Imagine copying it billions of times without losing the message. Is that design or inevitability? Some scientists say DNA is simply what works. Of all possible molecules, it is one that hits the sweet spot. Simple enough to form, complex enough to store meaning. Others wonder, could it have been something else? In the lab we've built synthetic versions of DNA, molecules with 6 or even 8 bases. Strange sugars, alternate backbones. They can work, they can copy, they can store information, but they are not found in nature. Not yet. So why 4 bases? Why this alphabet? There's no hard answer, only clues. 4 is the minimum number that allows redundancy and variation. Enough combinations for complexity, but not so many that the system collapses. With 4 letters you can build 64 codons, combinations of 3 bases. More than enough to encode all 20 amino acids, plus start and stop signals. It's just enough. No waste. No fluff. Even the helical twist itself is not random. It's the shape that minimizes energy, that allows access to internal sequences, that protects the genetic code from radiation. It's the form that folds easily, unfolds precisely, and nests into itself like a sleeping fern. In physics, we say systems seek low-energy states, forms that are stable, resilient. The double helix, it turns out, is a low-energy solution to a high-stakes problem. How to remember. That's what DNA does, above all else. It remembers. Not with consciousness, not with intent, but with form. Its structure preserves its message. Its bonds preserve its sequence. Its symmetry preserves its integrity. Even when broken, DNA can repair itself. Its paired strands allow copying from a backup. Its enzymes detect and fix errors. No machine we've built rivals its quiet consistency, and that raises an unsettling question. Could the laws of chemistry be biased toward meaning? Not conscious, not intelligent, but fertile. What if the double helix is not just a clever accident, but a recurring theme in the language of matter? What if, given carbon, water and time, this shape forms again and again? In distant oceans, beneath alien skies. It's possible. The logic of base pairing is universal. Hydrogen bonds, molecular geometries, charge distributions, these are not unique to Earth. And so maybe the double helix is not a one-time miracle. Maybe it is inevitable, like the spiral of a galaxy, like the symmetry of snowflakes, like the curl of a fern frond growing toward the light. In that case, we might not be alone in our molecular design. We might share our spiral with other life forms in other places, built from the same logic. And if that's true, then DNA is not just a molecule, it is a template, a blueprint the universe uses when it wants to remember. So as you lie here now, your breath steady, your cells quietly dividing, know this: inside you, the spiral turns. It coils and uncoils, unzips and rezips, endlessly reading and rewriting the script of your being. And that spiral, that elegant, silent staircase, may be more than your own. It may be part of something greater, a pattern, a signal, a signature repeated across planets, across time, too perfect to be chance. Perhaps not, but perfect enough to make you wonder. Imagine holding a single teaspoon of salt. Now imagine that inside that teaspoon, hidden in plain sight, is enough data to encode every book ever written, every film ever made, every heartbeat ever recorded by every human who ever lived. It sounds like something out of science fiction, yet when it comes to DNA, reality often surpasses the limits of our imagination. The molecule that defines us, that choreographs the ballet of life within each of our cells, is not just a string of instructions. It is a dense, meticulously organized archive, more compact than any storage system humanity has ever built. Every spiral of the double helix carries a payload of information so vast, so delicately ordered, that even our most advanced digital systems seem crude in comparison. A single gram of DNA can theoretically hold up to 2115 petabytes of data. That is 2115 million gigabytes. An amount so staggering that if you attempted to store the same information on traditional hard drives, you'd need a warehouse to hold them. Yet DNA does this within microscopic strands, invisible to the naked eye. This unparalleled efficiency is not just about density, it's about fidelity. DNA stores its information in a four-letter code, as we know: A, T, C, and G. These letters are not written in ink, nor pressed into magnetic plates. They are arranged through chemical bonds, forming patterns that persist through time, temperature, and pressure, preserved with a reliability that has astonished even the most skeptical scientists. Consider the discovery of DNA in the bones of ancient mammoths or Neanderthals, fragments hundreds of thousands of years old, tucked into fossils buried in permafrost or sediment, still legible, still whispering stories of tortures that once walked across ice-covered valleys or through sun-drenched grasslands. What other storage system, analog or digital, could survive millennia of chaos and still be readable? Even more impressive is the fact that this information doesn't merely sit idle. It is dynamic, living, and constantly accessed. Your body is reading and writing DNA every second of every day. It's an active script, consulted and revised as needed, with different chapters open depending on the cell, the function, and even the time of day. Liver cells flip to the pages about detoxification. Skin cells consult instructions on regeneration. Immune cells reference emergency protocols when threats are detected. And all of this happens in parallel, in billions of cells, seamlessly and silently. But perhaps the most breathtaking aspect of DNA's information density is not the quantity of data, but the way it is used. It isn't just about storage, it's about expression. Not every gene is activated in every cell. The body selects which pieces of the script to read, and when, with exquisite precision. This regulation is managed by a complex network of signals, epigenetic tags, transcription factors, and environmental cues, all working together to make sure the right proteins are made in the right place at the right time. Imagine a vast library where each book contains the full blueprint of a city, but each librarian only opens the pages relevant to their department. One flips to the section on electrical grids, another to plumbing, another to zoning regulations. DNA operates in a similar way. Every cell holds the same book, but reads only what it needs. And the beauty of this system is that it's not fixed. The pages aren't permanently marked or locked. The cell can shift its reading habits in response to new conditions. If you're exposed to sunlight, skin cells activate genes for melanin production. If you get sick, Immune cells upregulate genes related to inflammation. The script adapts. Now, let's return to the question of how this compares to our own technology. Consider the world's most advanced data centers. Vast complexes consuming megawatts of electricity, cooled by industrial fans, humming with the heat of servers stacked floor to ceiling. They store petabytes of data, yes, but they're limited by size, energy, and materials. DNA, by contrast, stores data passively. It requires no electricity to maintain its sequence. Once written, its code can persist in dry, stable conditions indefinitely. Researchers have already demonstrated the ability to store digital files, including images, books, and even movies within synthetic DNA strands. Encoded, stored, and later retrieved with nearly perfect accuracy. One experiment encoded an entire operating system, a short film, and a 1948 research paper into a few micrograms of DNA. Another stored a full computer virus, music files, and a vintage video game. When retrieved, the data was fully intact. This isn't a theoretical possibility, it's a working reality. And it has caused some scientists to speculate that future civilizations may store their histories not on chips or disks, but within synthetic genomes, folding libraries into molecules. Now hold that thought, because here's where it gets stranger. If DNA is capable of storing information so efficiently, so durably, with such elegant architecture, why stop at Earth? What if this molecular system is not just terrestrial? What if it's universal? The informational efficiency of DNA has prompted some to wonder whether life beyond Earth, if it exists, might use similar structures. After all, the laws of chemistry are not confined to our planet. Base pairing, hydrogen bonds, molecular helices, these are not Earth-specific inventions. They are rules of matter. So, when we search for alien life, we might not be looking for green creatures or flying saucers. We might be looking for a familiar twist, a double helix, a chemical script, an alien genome written in something uncannily like our own. Could panspermia, the theory that life began elsewhere and was carried to Earth, be tied to the resilience of DNA? If so, DNA's structure isn't just efficient, it's transportable. It can survive extreme heat, cold, radiation. It can persist in meteorites, in dust, in deep space. If life did travel here, DNA would have been an ideal messenger. And so we return to our earlier image. The spiral. Not just a symbol of life, but a vessel for knowledge, curled into the nucleus of a cell, curled into the potential of the cosmos. A helix that may be more than our own. Inside that spiral, every letter, every pairing, every fold carries not only your genetic code, but perhaps a code much older, maybe even a message. A cosmic pattern repeated across the universe wherever chemistry allows memory. It's humbling. And as you lie there, resting, your body slowly unwinding, remember that within you is a story told in a language older than words. And that story is written on the densest scroll ever conceived, one that folds galaxies of information into a single cell. And so the question lingers in the quiet: is DNA just a molecule, or is it the universe's preferred way of remembering? Let that thought sit beside you tonight, as your cells continue their silent work, reading from a book you never consciously open, but that is yours alone, and yet strangely familiar. In every cell of your body, nestled between genes for muscle repair, or vision, or metabolism, there are ancient codes that whisper stories of something foreign. They don't behave like typical genes. They don't even belong entirely to us. They are fragments of viral DNA, old infections frozen in time, stitched into the human genome like forgotten footnotes in an epic that began long before memory. And the number is staggering. Nearly 8% of the human genome is made up of these endogenous retroviruses. That's more than all the protein-coding genes combined. These viral remnants are not invaders anymore. They've been co-opted, fossilized. Sometimes silent, sometimes awakened, and always present, like the DNA version of ghost stories passed down in molecular whispers. To understand how they got there, we need to imagine a time, billions of years ago, when Earth was not yet a place of forests or oceans or oxygen, but of searing heat and ceaseless collisions. In that raw, chaotic world, life was struggling to take root, and viruses, if they existed at all then, were the mysterious couriers of genetic material, shuttling information from cell to cell, like rogue messengers without allegiance. Retroviruses operate differently than most viruses. Instead of simply hijacking a cell to replicate, they integrate their genetic material into the host's DNA. They become part of the host, threading their code directly into the genome. When this happens in somatic cells of the body, the effects are limited. But when it happens in germline cells, eggs or sperm, the virus becomes part of the next generation. It's no longer just a visitor, it becomes inheritance. Over time, these viral sequences mutate, decay, and lose their ability to function as viruses, but their shadows remain, embedded in the genome, sometimes doing nothing at all, other times influencing gene expression, and in rare moments, becoming crucial. For example, one of the genes essential for placenta formation in mammals, including humans, originated from a viral gene. A virus, long extinct, donated a piece of code that eventually helped make pregnancy possible. That which was once an infection became a necessity. So we must ask, if viruses can rewrite the rules of biology, if they can donate code that becomes part of us, are they just accidents, or were they messengers? It's a question that grows more provocative when we realize that viruses aren't exactly alive in the traditional sense. They don't breathe, they don't metabolize, they don't reproduce on their own. They exist in a strange in-between space, packets of information wrapped in protein, waiting for a host to awaken them. They blur the line between chemistry and biology, between code and consciousness, and they are everywhere. In the oceans, viruses outnumber all other forms of life. In a single drop of seawater, there may be more viral particles than people on Earth. They infect bacteria, algae, fish, whales, everything. And in doing so, they move genes around. They're nature's editors, snipping, pasting, repurposing, remixing the scripts of life. Some researchers believe that viruses may be older than cellular life itself, that perhaps they are relics of a pre-cellular world, ancient strands of code, born from the primordial soup, still searching for something to latch onto. And if that's true, then the origins of life and the origins of viruses are not two separate stories. They are chapters in the same strange book. Now imagine, just for a moment, that somewhere out there beyond Earth, beyond our sun, other planets formed, cooled, and cradled chemical soups of their own. And in those alien waters, strands of information began to coil. Perhaps their equivalent of DNA, perhaps something else entirely. What if those molecules too were infected, altered by viruses? What if panspermia didn't begin with a cell, but with a virus? A courier of code drifting through space on a rock, or a shard of ice. Not alive, not dead, just waiting. Waiting to land. Waiting to be read. It's not as improbable as it sounds. Scientists have already found microbes that can survive in space for extended periods. Extremophiles like tardigrades or spores of Bacillus subtilis have withstood the vacuum, the radiation, the cold, and viruses, being smaller and hardier in some ways, may survive even longer. Meteorites that have landed on Earth contain amino acids, the building blocks of life formed in space, so the idea that a viral particle, carrying information from another world, could have seeded Earth, is not only plausible, it's being taken seriously. And that brings us back to those strange viral sequences in our genome, the ones that don't quite belong, the ones that don't match anything we've seen in nature. Could a fragment of alien code be sitting quietly in our DNA, mistaken for a mutation or a mystery retrovirus? Could evolution have been nudged by something not entirely of this world? We don't have the answer, but what we do have is a growing sense that life as we know it is not an isolated miracle, but part of a broader pattern. A chemical inevitability shaped by physics, by chance, and perhaps by visitors too small to see, too old to trace. Even now, as you rest, billions of viral sequences in your body lie dormant. Some are silenced by methyl tags, molecular do not disturb signs. Others are active, regulating genes or influencing how your immune system responds to threats. Some, we suspect, might even protect us from other viruses, a kind of ancient rivalry playing out inside us. one viral ghost shielding us from another. The more we learn about these sequences, the more they challenge our definitions. What is self and what is other? Where does the line between host and invader truly lie? When the code of a virus becomes indistinguishable from the code of a human, is it still a virus? Or is it simply ancestry? This is the heart of the paradox, that what once threatened life became part of its architecture. That danger and design can be entangled, that the enemy of yesterday might be the blueprint of today. And perhaps nowhere is this clearer than in the very mechanism by which DNA replicate, the enzymes that unzip the double helix, that build new strands, that scan for errors and repair them. They too may have viral origins, molecular tools borrowed from invaders, repurposed by evolution, refined over billions of years. In this way, viruses are not just footnotes in the story of life, they are co-authors. Now picture this, a single retrovirus, ancient and unknown, embedding its code into the DNA of a distant ancestor. That code, copied faithfully through generations, reaches you. It is inside your skin cells, your neurons, your lungs. It does not speak, but it waits. And maybe, just maybe, in some distant galaxy, on a world circling another star, a different life form has its own viral fossil, its own ancient infection, its own lingering trace of the same message, a resonance, a shared echo. Perhaps that is how the universe remembers itself. Not through stars or galaxies, but through the soft imprint of viral code, tucked quietly inside the living. So when we ask whether DNA came from Earth or somewhere else, the truth might be both. DNA is a structure born of Earth's chemistry. Yes, but shaped, altered, and whispered to by messengers that may have traveled far, messengers that still sleep inside you. Tonight, as your breath slows and the mind begins to drift, think of those silent fragments folded into your genome. Think of the code within the code. The alien within, not threatening, not foreign, but foundational. A reminder that the story of life is not written in isolation. It is a patchwork, a mosaic of encounters, some so ancient they no longer have names. And in the quiet of your resting body, that mosaic continues to shimmer. Part earth, part stardust, part virus. And perhaps, just perhaps, part something else. Let your cells hold that wonder for you, as sleep wraps you in its own code of dreams. Picture a world where instructions are not typed, not spoken, not even drawn, but encoded in chemistry, where meaning isn't carried in words but in the shapes of molecules, where messages are passed, not between people but between proteins, passed in silence, carried in spirals and loops. This is the world inside you, and at the center of it is something far stranger than language. It's code, but not just any code. DNA is not only the blueprint of your body, it is the programming language of life itself. Not metaphorically, literally, because at its core, DNA behaves like a software language. It has syntax, it has logic, it follows rules, and those rules are what have made every cell, every organ, every sensation you've ever felt possible. But what if DNA is more than just an internal code? What if it's not only written for biology but by design, meant to be read? Let's begin with the basics. The part we know. DNA stores instructions using 4 nucleotide bases, adenine, cytosine, guanine and thymine, arranged in long strings. Each of these sequences encodes for something specific. Change the sequence, and you change the outcome. Swap a G for a T in the right place, and instead of brown eyes, you get blue. But go further, and you start to see patterns, literal programming patterns. Codons, groups of 3 bases, act like words in this language. Each codon corresponds to an amino acid, and amino acids are the building blocks of proteins. In the same way, binary code in a computer translates to commands on a screen. DNA code translates into biological functions. Even more eerily, DNA has redundancy, like error correction code in computer science. Several different codons can code for the same amino acid, offering protection against mistakes during copying. That's not just nature being clever, that's programming logic, protective, anticipatory, and deeply intentional. But this is where things get even stranger. Because when scientists began to look deeper into the structure and organization of DNA, they noticed something uncanny. They found non-coding regions, stretches of DNA that don't directly code for proteins. These areas were once dismissed as junk, meaningless leftovers of evolution. But that interpretation has since changed. These regions, it turns out, may control how genes are expressed, how they're timed, suppressed, or activated in response to signals. In programming terms, they act like scripts and conditions. If this, then that. They're the logic gates of biology. DNA isn't just static storage, it's dynamic. It has loops, conditionals, nested systems, just like a program. It stores instructions, it runs them, and it modifies them over time. And some scientists have begun to wonder, if DNA behaves so much like a programming language, could it be one? This is not to suggest someone wrote it like an engineer writes software, but it raises the question, how do instructions arise so cleanly, so efficiently, and in so universal a format across all life forms? Because here's what's curious. DNA's structure is universal. Every living thing, plants, animals, bacteria, fungi, uses the same code, the same 4 bases, the same triplet codon structure, the same start and stop signals. From humans to sea slugs to algae drifting through ancient oceans, it's one language spoken in countless dialects. Why? Why does nature converge on one code? Computer programmers will tell you there are dozens of ways to write the same program. You can get the same output using different syntax, different logic. And yet DNA, across billions of years, clings to this one design. Why not something else? This isn't just curiosity. It's a riddle. Because DNA doesn't have to look the way it does. In theory, life could use different molecules, different base pairs, but it doesn't. And that uniformity, so specific, so consistent, feels odd. That's when some began to ask the unaskable. What if DNA isn't just a product of Earth? What if its language was seeded here? What if this isn't a random outcome, but a chosen structure, optimized, universal, and left behind not by evolution alone, but by something more ancient? We already know that simple molecules, amino acids, the precursors to life, can form in the cold darkness of space. Meteorites have delivered them. Comets are dusted with them. And if those molecules carried the seeds of the DNA code, if the language of life predated Earth's first cell, then it changes everything. DNA wouldn't just be a biological molecule, it would be a message, a protocol, a kind of software installed on every form of life that emerged here. Which raises the most haunting question of all: who wrote the first line? Was it chemistry, chaos, or intention? And before you dismiss this as wild speculation, consider how humans have begun encoding digital data into synthetic DNA. Scientists have stored books, videos, even AI training models into strands of DNA, retrieving them later with perfect accuracy. If we can do that now, could something somewhere else have done it long before? This brings us to a theory known as biological SETI, the search for intelligent signals not in space but in our cells. The idea is simple. If an advanced civilization wanted to leave behind a message that could survive time, war, entropy, and extinction, where would they put it? Not on stone, not on metal, but inside life. They might encode their message inside a structure like DNA, a self-replicating, self-preserving molecule carried forward by evolution, unread for millennia, until the species it seeded became curious enough to look inward. This is speculative, yes, but it's also testable. Some researchers have begun analyzing non-coding regions of DNA, looking for patterns that defy evolutionary randomness, for mathematical signatures, for data compression, for prime number sequences, even binary code. So far, nothing definitive has been found, but the fact that we're asking these questions, that the code inside your cells is so elegant, so rich, so resilient, that it invites comparison to software, says something extraordinary about DNA. Whether written by chance or by mind, its structure is indistinguishable from design. And maybe that's enough to give us pause. Maybe it means that life in all its complexity is not a random accident, but a phenomenon that can arise wherever the right patterns emerge. Maybe DNA is just one version of this pattern. Maybe there are others, Codes we don't yet recognize waiting in alien cells, drifting through frozen oceans beneath the crust of moons, or floating quietly in the clouds of a far-off exoplanet. Or maybe, just maybe, it's all one code. One syntax used across the universe, modified, evolved, but fundamentally the same. Not because it's the only way life could exist, but because it's the best way. Because information wants to live. And DNA is how it lives. So tonight, as your thoughts begin to drift and the quiet hum of your body continues its nightly repair and renewal, think of the code inside you, not just as a biological marvel, but as a sentence in a language you don't speak, but somehow understand. A script that doesn't just make life possible, but readable. You are not just a body. You are code. You are logic. You are a message, still running, and somewhere, perhaps not just here, someone, or something, may be reading the same language. Ask ChatGPT. Before the first creature swam, before the first cell divided, before even Earth itself had fully cooled from its molten beginnings, something extraordinary may have already been unfolding in the shadows of chemistry. A whisper, not of life, but of potential. A message written not in words but in patterns, in logic, in symmetry, in the prelude to biology. There may have already been a code, waiting patiently in pools of ancient molecules. This is the puzzle scientists have come to call the prebiotic world, the mysterious realm that existed before biology officially began, yet somehow gave birth to it. And at the heart of this mystery lies a question so fundamental, so elusive, that even now it keeps some of the world's brightest minds awake at night. How did information arise before life existed to interpret it? Because that's what DNA is. Not just a molecule, not merely a chemical compound. It is information, arranged, structured, logical, persistent. But how did such complexity emerge from the chaos of early Earth? Or more unsettling still, did it even originate here? The classic theory is ababiogenesis, the idea that life emerged spontaneously from non-life, through a gradual buildup of organic molecules that eventually learned to self-replicate. Under the right conditions, heat, water, certain minerals, atmospheric gases, organic molecules could assemble themselves into more and more complex configurations. This theory gave us experiments like Milowori, which in 1953 demonstrated that amino acids could form under simulated early Earth conditions. Encouraging, yes, but amino acids are not life. They are its alphabet. Useful, but silent, until arranged with intent. The problem is that random molecules, no matter how plentiful, don't spontaneously start encoding complex instructions. You could fill oceans with amino acids, and they wouldn't leap into a double helix. Something more is needed, not just matter, but structure. Not just ingredients, but syntax. So where did that structure come from? One line of thought points to RNA, the molecular cousin of DNA, as the original architect. This is the basis of the RNA world hypothesis. The idea that before DNA, before proteins, life's first spark may have come from strands of RNA that could both store information and catalyze reactions. Unlike DNA, which mostly stays in the liver, RNA could step out onto the factory floor and help build the tools it needed. Imagine that, molecules that not only remembered their shape, but helped build it again. Tiny chemical pioneers, looping and folding into shapes that nudged other molecules into place. Some scientists have even discovered RNA molecules called ribozymes, essentially enzymes made of RNA, capable of catalyzing reactions like their protein cousin. A glimpse perhaps into a time when the instructions in the builder were one and the same. But here's where the thread gets more tangled. To build RNA, you need nucleotides. And to build nucleotides, you need a precise sequence of chemical steps that frankly don't happen easily under most natural conditions. Laboratory simulations have managed to coax these steps along, but only under carefully crafted circumstances, often requiring pure starting materials and controlled environments. Not exactly the bubbling chaos of early Earth. And so, the mystery deepens. How did RNA form? If it's too delicate to arise naturally and too complex to emerge randomly, are we missing something? A chemical shortcut we haven't yet seen? Or was there a different kind of information altogether before RNA? A more primitive code we no longer recognize, lost to time? Some researchers now wonder whether genetic information itself, the logic behind base pairing, the symmetry of double strands, the self-correcting elegance of the code, might have deeper roots not just in biology, but in physics. That perhaps the ability to store and replicate information isn't a biological invention but a physical principle. Think about crystals, snowflakes, patterns in sand dunes, the spiraling arms of galaxies. The universe favors symmetry. It loves repeating structures. Could DNA be a natural extension of this tendency? An expression of the cosmos' bias toward organization? This line of thinking leads to a provocative idea that the information structure of DNA is not a random invention, but a universal language, one that could arise anywhere the right conditions are met. Not just Earth, not just here. And this is where the theory of panspermia returns. Not as science fiction but as a potential solution to the information paradox. If the odds of DNA forming from scratch are impossibly low, if Earth was too young, too chaotic, too fast, then maybe life didn't start here at all. Maybe it arrived. Imagine microscopic couriers, bacterial spores, viral particles, fragments of encoded polymers, tucked into comets or meteorites, drifting through space like seeds on a cosmic wind. Frozen, silent, shielded from radiation by rock and ice. Perhaps for millions of years, until one day, somewhere in the vast black, gravity pulled them into a warm young world with water, atmosphere, and the spark of sunlight. A landing, not a birth. And if that's true, then the structure of DNA, the way it pairs, coils, replicates, may not be Earth's invention. It might be the universe's, the standard template for life wherever it arises. That would mean the code we carry in every cell, those A's and T's, those C's and G's, aren't just our own. They're ancient. Perhaps far older than Earth itself. Even more mind-bending is the idea that this code might be discoverable through math. Some scientists have begun exploring whether the genetic code has properties of error-correcting algorithms, similar to those used in computer science. That is, not only is DNA efficient and elegant, it may contain embedded checksums, redundancy, even compression. All hallmarks of designed systems, or at the very least, systems shaped by information pressure over unimaginable spans of time. Could it be that the genetic code evolved, not just for survival, but for efficiency? That natural selection didn't just favor organisms that lived, but codes that endured? And what if life elsewhere on Europa, on Titan, in the clouds of Venus, uses similar principles? Not the same sequences, perhaps, but the same logic: base pairing, replication, information encoding. What if the universe doesn't just support life, it encourages repetition of its blueprint? We often think of DNA as our personal identity, our link to family, to ancestry. But zoom out, widen the lens. If this code is written into comet fragments, tucked into interstellar dust, looping through the vacuum in dormant strands, then DNA becomes something else entirely. It becomes a signature, not just of humans, not even of Earth, but of the universe itself. That would mean when we study genetics, we're not just decoding ourselves, we're reading a dialect of the cosmos, a dialect that may echo in other skies, other worlds, other oceans beneath ice. It is a thrilling, dizzying thought, and perhaps a humbling one too, because it suggests we are not unique in our chemistry, only in our perspective, that we are participants in a story much older than our species, much older than our sun. And so as you settle deeper into the quiet, let this possibility surround you gently, like starlight. That long before there were names, long before there were lungs to breathe, or eyes to witness, the universe may have already been writing, in base pairs, in patterns, in promise, and perhaps it still is. In the grand architecture of DNA, not every stretch of code is meant to build. Some are meant to whisper, some are meant to silence, some are meant to wait. Quiet sentinels perched in the dark, watching, adjusting, fine-tuning. These are not the genes that form muscle or pigment, or enzymes. These are the genes that control the builders themselves. They do not lay bricks. They draw the blueprints. They are the regulatory genes. And in many ways, they hold the true power. When people think of DNA, they often imagine it as a static blueprint, a one-time set of instructions passed down from parent to child, left to sit passively within our cells. But DNA is not passive. It listens, it reacts, it adapts, and much of that responsiveness lies in the realm of gene regulation. Regulatory genes are like switches scattered throughout the genome, but they don't just turn things on or off. They shape when, where, and how strongly certain genes are expressed. Think of a symphony orchestra. Structural genes are the instruments, each with their unique sound and purpose. But without a conductor, even the finest violin would screech or fall silent. Regulatory genes are that conductor. They raise a baton, signal a pause, or summon a crescendo, and sometimes they choose silence. Take homobox genes, for instance, a class of regulatory genes so ancient and powerful that their echoes can be found in everything from humans to fruit flies. These genes determine the body plan of an organism, where your arms go, where your eyes form. They operate like cosmic draftsmen, sketching the axis of symmetry before you ever take your first breath. Mutations here can be devastating, like rewriting the script of a play halfway through opening night. Then there are the enhancer and silencer regions, short, non-coding sequences that can dramatically boost or dampen the expression of a gene. Enhancers don't have to be close to the genes they affect. Sometimes they're thousands of base pairs away, looping through the genome's folded landscape like invisible puppeteers, pulling strings from afar. And silencers, as the name suggests, hush expression when needed, preserving balance, keeping chaos at bay. But the orchestra doesn't play in isolation. It takes cues from the world outside. This is where the environment meets genetics in the most delicate of dances. External factors like temperature, stress, diet, toxins can influence gene expression through a process called epigenetics. This doesn't change the DNA sequence itself, but rather how accessible or active certain parts of the genome become. Chemical tags, such as methyl groups, latch onto DNA and alter its behavior, like slipping a note to the conductor. Quieter, here, louder, there. It's the reason identical twins, born with the same genetic blueprint, can develop different traits over time. As they live, their environments nudge their genes in different directions, turning up the volume in one life while muting it in another. One twin might develop asthma, the other doesn't. One grows taller, the other more resilient to stress. The genetic code remains the same, but the interpretation changes, and sometimes those changes echo across generations. That's the haunting power of transgenerational epigenetics. The idea that your grandmother's famine, your grandfather's war trauma, might leave tiny chemical bookmarks on their DNA, bookmarks that were passed to your parents, and then to you. It suggests memory lives, not just in the brain, but in the genome itself. That what we survive doesn't merely end, it writes itself into us. Of course, the genome isn't always so poetic. Regulation can also go awry. When regulatory genes malfunction, the consequences ripple outward. Cells may begin dividing uncontrollably, ignoring the usual stop signals. Genes that should be quiet roar back to life. Others, crucial for repair, go mute. The result can be cancer, developmental disorders, autoimmune disease. It's not always the structural gene that's flawed. Sometimes it's the conductor who's lost the score. One of the most studied examples is the p53 gene, often called the guardian of the genome. This regulatory gene plays a critical role in preventing damaged DNA from being passed on during cell division. It can halt the cycle, call for repairs, or initiate cell death if things go too far. But if p53 itself is mutated, the whole system can spiral into chaos. Cells ignore damage, mutations accumulate, tumors grow, but regulation is not always about survival. Sometimes it's about identity. In embryonic development, gene regulation is what turns a single fertilized egg into trillions of specialized cells. Skin, muscle, neurons, bone, every one of those cells contains the exact same DNA. But they read it differently, express different genes, respond to different signals. The regulatory code is what makes a neuron, and not a fingernail. Even in adulthood, your cells continue this dynamic dance. Your immune system activates specific genes only when a virus invades. Your liver shifts gene expression after a glass of wine. Your brain adjusts neurotransmitter regulation after a sleepless night. The genome is not a script. It's a responsive screenplay, constantly being edited in real time. This adaptive regulation also explains some of the mysteries of aging. As we grow older, our gene regulation becomes less precise. Silencers forget their cues. Enhancers fire at the wrong time. Epigenetic marks fade or pile up in the wrong places. It's as if the conductor becomes weary, the baton trembles, and the symphony begins to fray. Some genes become overexpressed, others underutilized. Repair slows. Inflammation lingers. Balance becomes harder to maintain. And yet, some researchers believe this process might be reversible. Experiments with reprogramming cells, turning adult cells back into stem cells, have shown that you can reset the epigenetic clock. Genes long silenced can be awakened again. Damaged regulatory patterns can be rewritten. So, glimpse of what regenerative medicine might become. Not just patching wounds, but teaching the genome to remember youth. But it's not only scientists who harness gene regulation. Viruses do too. Some viruses insert their genetic material into our genome and lie dormant for years, waiting for the right moment to reactivate. The herpes virus, for example, can remain silent in nerve cells, invisible to the immune system, until stress or illness triggers its return. HIV does something similar, integrating into host DNA and manipulating regulatory pathways to survive. Even more strangely, ancient viruses from our evolutionary past still lurk in our genome. Roughly 8% of human DNA comes from retroviruses that infected our ancestors millions of years ago. These viral remnants are mostly inactive, but not always. Some have been co-opted for human function, helping with things like placental development. Others occasionally flicker to life under specific conditions. In a way, our regulatory system doesn't just manage our gene. It also policies ancient invaders that became permanent residents. The genome is not just a code, it's a civilization. Some regions are bustling cities, genes expressed constantly, maintained with care. Others are quiet villages, activated only during emergencies. Some are ruins, sequences left abandoned by evolution, still watched just in case. And scattered throughout this landscape are the regulators, the lawmakers, the architects, the sentinels, guiding the rise and fall of biological empires. So as you drift into rest tonight, picture not a string of code, but a vast illuminated manuscript. Its pages don't just hold instructions, they hold intention. They know when to whisper, when to shout, when to wait in silence. And in that silence lies the deepest complexity of all. Because life isn't just about what is written, it's about what is read. And who, or what, is reading it. Let that thought echo quietly through your own cells tonight. Let's imagine a lab somewhere in the world, dimly lit, humming with quiet electricity. Inside, a vial of dust rests on a steel tray. Harvested not from Earth, but from a meteorite that fell through our skies. A piece of the cosmos delivered right to our doorstep. Within that dust might lie the oldest molecules we've ever touched. Maybe even a whisper of something once alive. It's here, in moments like this, that science starts to lean into poetry. Because the real question isn't whether life exists elsewhere in the universe, but whether its code would look anything like ours. DNA is often treated as a miracle, and rightly so. But is it a universal miracle? Could life on another planet be written in the same four-letter alphabet? A, T, C, and G? Or would it use different rules entirely? New letters, strange bonds, unfamiliar helices? To ask if DNA came from Earth, or somewhere else, isn't just to ask about origins. It's to ask about echoes, patterns, whether life elsewhere might rhyme with our own. Many scientists now think that life's building blocks might be cosmic in origin. Amino acids, the precursors of proteins, have been found in meteorites, comets, and interstellar dust. These molecules aren't rare, they're everywhere, floating between the stars, embedded in planetary rings, carried on ancient rocks. When the early Earth was still molten and wild, comets may have bombarded its surface with these basic ingredients. Not instructions yet, but the alphabet. the raw letters waiting to be strung into meaning. If these molecular travelers seeded our planet, they might have done the same elsewhere. Mars, Europa, Titan, planets we can see through telescopes, and moons wrapped in icy shells. Are they lifeless? Or are they simply unrid? Here's the strange part. If life did arise on other worlds, it might not look alien at all. Not at the microscopic level. The double helix might not be Earth's invention. It might be chemistry's best solution. The structure is stable, compact, self-replicating, and incredibly efficient at storing information. It's not hard to imagine evolution stumbling upon similar solutions in other parts of the cosmos. Not because they copied us, but because the laws of chemistry gently nudged them in that direction. It's like snowflakes. No matter where they fall, they share a hexagonal pattern, because that's how water molecules arrange themselves under certain conditions. Maybe life's code works the same way, and maybe DNA, or something eerily similar, emerges again and again in the universe. Not because it's unique, but because it's inevitable. There's even a field of study called astrobiology devoted to questions like this. It blends biology, chemistry, planetary science, and astronomy into one grand inquiry. What does life look like elsewhere? And how would we know it if we saw it? The trick is, we can't assume that alien life will look like humans, or animals, or trees. We have to start smaller, more fundamental. We look for signs of metabolism, patterns of energy exchange, structures that maintain themselves, reproduce, adapt, and increasingly we're scanning for signs of encoded information, because encoding is one of life's trademarks. If a molecule contains a sequence that stores instructions, that's a strong hint we're not looking at geology anymore. We're looking at biology. NASA and other space agencies are already experimenting with tools to scan for such molecular patterns on future missions. They're developing instruments that could land on Europa or Enceladus and test ice cores anything that resembles base pair structures. They're programming probes to detect molecules that resemble nucleotides or their functional equivalents. And here's where things get even more tantalizing. Some scientists have designed synthetic alternatives to DNA. These molecules use different sugars or base pairs, but can still store and transmit information. They still spiral, still replicate. They're called XNAs, cyanonucleic acids. And they're proof that DNA isn't the only way to write life's code, just the way it happened here. So when we ask whether DNA came from Earth or somewhere else, we're also asking whether it had to be DNA at all, or whether the universe allows multiple dialects. Maybe Earth speaks in ATCG. Maybe another world writes in unfamiliar letters, but with familiar rhythm, a different tongue, but the same kind of music. Panspermia is the theory that life began not on Earth, but arrived here from space. It doesn't explain the origin of life. It just pushes the starting line back further, out into the stars. Some versions of panspermia are passive. Life hitches a ride on comets or meteorites. Others are more speculative, involving intelligent seeding, life deliberately spread by advanced civilizations. But at its core, the idea suggests that life's building blocks, or even full microbial life, can survive interplanetary travel. And remarkably, lab tests support this possibility. Certain extremophiles, microorganisms that thrive in harsh environments, have survived exposure to space. They've endured vacuum radiation and temperature swings. Tardigrades, for example, tiny water bears with stubby legs and strange faces, have been shown to survive the vacuum of space. In theory, small organisms encased in rock could survive a journey across planets, protected from heat and radiation. So maybe DNA or something like it didn't originate here. Maybe it crash-landed, bounced, took root. Maybe the first strands of life's code were written not in Earth's warm ponds, but in the cold silence between stars. If true, that would make every living thing on Earth an alien in origin. Every tree, every fish, every child, descendants of a cosmic journey. And it raises a haunting possibility. Maybe the universe is not full of isolated life forms, each arisen in isolation. Maybe we are all fragments of the same beginning, different branches of one long stellar script. It also means we could recognize alien life, not just by what it looks like, but by how it stores memory. If we found a double helix on another world, or even a twisted chain with equivalent function, It would suggest a kind of convergence, different origins, same solution. And that, perhaps, is the most hopeful idea of all, because it means we're not alone in our biology. We're not isolated miracles. We're part of a pattern. As you rest, think about that pattern, the way your cells wind and unwind strands of memory, the way your breath carries the byproduct of billions of years of molecular evolution, the way your DNA in all its microscopic grace might not just be human, it might be universal. In the silence of night, let that possibility breathe with you. Let it thread through your thoughts like a strand of code waiting to be read. Somewhere out there, in the quiet dark, another world might be spinning, another helix might be turning. And if it is, then the universe doesn't just contain life, it remembers it. And maybe that memory, that spiral, is the most beautiful language ever written. Beneath your skin, inside every cell, lies a memory far older than your life, older than civilization, older than mammals. It is a fossil made not of stone, but of sequence. It is your DNA, and buried within its spiraling strands are echoes of the creatures that came before you, whispered remnants, ancient signatures, footprints of time that never hardened into rock, but instead curled themselves into code. This chapter is about the past, not just your personal ancestry, but the molecular inheritance shared by all life on Earth. Because DNA doesn't forget, it carries forward the instructions that have proven themselves useful across millennia. It is both the record and the result of survival. Some genes have been passed down, almost unchanged, for hundreds of millions of years. These ultra-conserved sequences are like sacred lines in a manuscript, so crucial to life that any mutation would be lethal. They exist in humans, fish, birds, worms. They thread through the tree of life like a golden strand of common memory. Other parts of the genome are messier, patched, copied, broken, repurposed. They bear the scars of battles with viruses, of environmental stress, of evolutionary detours. But even these segments are valuable. They are the forgotten verses that tell us not just where we came from, but what we overcame. Scientists now study these genetic fossils to reconstruct the story of life. Phylogenetics. The study of evolutionary relationships lets researchers compare genomes across species and build family trees of astonishing resolution. By mapping shared sequences and tracing their divergences, we can estimate when two species last shared a common ancestor. We can visualize life's great branching timeline. You might be surprised to learn how much DNA you share with other creatures. Roughly 98% of your genes are identical to those of a chimpanzee, but you also share about 85% with a mouse. Even fruit flies, those tiny companions of rotting fruit, share over half their genes with you. And yes, even a banana shares about 60%. Life, it turns out, is not as separate as it looks. That's because evolution builds on what already exists. It doesn't start from scratch. It edits, repurposes, repeats. It's why a gene involved in building the eyes of a squid might also appear in a human, not because we are closely related, but because that gene worked. It solved a problem, so it stayed. Sometimes, entire gene families arise through duplication. A gene might accidentally copy itself, and the extra version is free to mutate, experiment, and evolve new functions. Hemoglobin, the molecule that carries oxygen in your blood, is part of such a gene family. Its ancestors go back to a time before vertebrates had blood, as we know it, and yet here it is, still at work in every breath you take. The genome also holds ghosts. Pseudogenes are remnants of once functional genes that were silenced by mutations. They no longer produce proteins, but they remain, like half-erased notes in the margins of a manuscript. These pseudogenes tell of past needs, enzymes we once used to digest different diets, defenses we once required against ancient threats. And then there are the viral fossils. Retroviruses, like HIV, insert their genetic material into host DNA. Occasionally these viral sequences end up in egg or sperm cells and get passed down to offspring. Over generations they lose their ability to replicate, but they remain molecular stowaways in the genome. In humans, these endogenous retroviruses make up about 8% of our DNA. That's more than all our protein-coding genes combined. Some of these viral sequences have even been co-opted by our bodies. One, called syncytin, plays a crucial role in the formation of the placenta. Think about that. A gene that once belonged to a virus now helps create human life. The boundary between self and other, between foreign invader and essential function, is not always so clear. Geneticists call this phenomenon exaptation, when a trait evolves for one function and is later repurposed for another. Feathers, for example, likely evolved first for temperature regulation or mating displays, only later becoming tools for flight. In the genome, exaptation is everywhere. Sequences that began as junk or virus, as error or accident, are reimagined as tools, signals, scaffolds for something new. Even jumping genes, transposons that can move around the genome, once considered mere genomic noise, have been found to play roles in regulating gene expression. They can turn genes on or off, influence development, or contribute to brain plasticity. Your mind, quite literally, may depend on the restless dance of ancient code. This shifting, layered history within the genome leads us to a sobering insight. You are not just a product of your genes, but of the history they encode. Every cell in your body is a library of evolutionary decisions. Some were triumphant, others were desperate improvisations. But together, they brought you here. It also means that inside you, buried in silence, are the blueprints of things that no longer exist. Genes from creatures long extinct. Instructions for bodies that never walked the earth. Potentialities that never emerged. The genome is not just a map of what is. It is a ghost story. As we continue decoding these stories, we're also learning to rewrite them. Gene editing technologies like CRISPR allow scientists to cut, delete, or replace sections of DNA with incredible precision. What once was fossilized can now be revived or redesigned. We are beginning to edit, not just disease out of the genome, but to imagine new traits, new enhancements. The ethics of this are complex, but the power is undeniable, and with that power comes responsibility. Because if DNA is a fossil, it is also a foundation, fed too carelessly, and we risk collapsing the intricate structure built over eons. But with care, with reverence, we may learn not only to preserve life but to extend it, to strengthen it. As you rest tonight, think of the code within you, not as static, but as living memory. Every strand, a sentence written by time. Every gene, a whisper from the past. You are not just made of star stuff. You are made of survival, adaptation, imagination. And maybe, just maybe, the next chapter of life's story is already waiting, hidden in some silent corner of your DNA, ready to be read aloud. Close your eyes for a moment. Imagine your body not as flesh and blood, but as a vessel built entirely from memory. Every breath you take, every movement of your fingers, every spark behind your thoughts, echoes of a code that remembers. DNA does not simply hold the blueprint of life. It remembers trials, triumphs, mistakes, and miracles. It whispers through the generations, not in words but in pattern and persistence. In this chapter, we step away from the microscope and into something more intimate. How DNA stores not just biological instructions, but the silent memory of survival. In its spiral staircase of nucleotides lies a story so vast, so intricate, that even now, we have only begun to read its opening lines. Inside your cells are genes that protected your ancestors during famines. Genes that helped them digest new foods, tolerate new climates, resist new diseases. Each of these genes was shaped not in comfort, but in hardship. The cold, the hunger, the fear, they left fingerprints on your biology. You carry the legacy of what your ancestors overcame. The sickle cell gene, for instance, is common in regions plagued by malaria. In its homozygous form, it causes a painful disease. But in its heterozygous state, it provides resistance to malaria, a brutal compromise carved into the genome by centuries of selective pressure, memory, encoded not in history books, but in the blood. And it's not only resistance to disease. Some populations carry genes that allow them to thrive at high altitudes, like the Tibetans who live among thin air, their bodies finely tuned to oxygen scarcity. Others have adapted to Arctic cold or tropical humidity. The genome responds. It adjusts. It remembers. But memory is not just what is passed on. It is also what is silenced. There are genes in your body right now that are dormant, silenced through a process called epigenetics, chemical modifications that do not change the DNA sequence, but affect how genes are expressed, like bookmarks in the code. These markers tell the cell which chapters to read and which to skip. And epigenetics is not fixed. It responds to the environment, to stress, to nutrition, to trauma. Experiences can leave chemical marks on DNA that persist across generations. In this way, even your grandparents' struggles may echo in your biology. One famous study examined children born during the Dutch hunger winter of 1944-45. Those who were in utero during the famine carried epigenetic changes that affected metabolism, growth, and health. Decades later, they inherited not just DNA, but the memory of starvation. We are only beginning to understand the full implications that stress, poverty, violence, and even emotional wounds might ripple forward, not just through parenting and culture, but through biology itself. That trauma might embed itself in the body's very instructions, and healing might require rewriting more than just the mind. This idea blurs the line between biology and biography, between what happens to us and who we become. The genome is no longer a static text. It is a dynamic journal, annotated, erased, rewritten, always becoming. And if this is true, if DNA remembers the echoes of experience, then perhaps memory itself is deeper than neurons. Perhaps it is molecular. Even in the brain, memory formation requires proteins. New experiences trigger gene expression, neurons communicate, synapses strengthen, and all of it, somewhere deep inside, begins with a strand of DNA being read in a precise, responsive way. The biology of memory is memory of biology. So when you recall a childhood smell, or the face of someone you lost, you are also invoking molecules, triggers, tiny dances of transcription and translation. You are not just remembering in your mind, you are remembering with your body. Some scientists believe that aging, too, is a kind of accumulated memory, that our cells, after years of responding to stress, toxins, UV light, and replication errors, begin to lose coherence. Epigenetic drift. Telomere shortening. The code phrase not just because of time, but because of what time brings. This concept has inspired researchers to explore ways to reset the genome, to remove epigenetic marks, and restore a more youthful expression profile. Early experiments in mice have shown promise. Rejuvenated tissues, extended lifespan, as if by clearing the molecular memory, the body remembers how to be young. Of course, we tread carefully. The same mechanisms that erase aging can unlock cancer. The genome is a delicate archive, and too much editing risks damaging what must be preserved. Still, the implications are profound. If we can truly read and write the memory of our cells, we may one day treat diseases before they manifest, heal trauma before it scars generations, understand ourselves not just as isolated individuals, but as chapters in a much longer living book. And it is living. That's the part we forget. Even as you sleep, your DNA is active. It is copied, repaired, regulated, transcribed. Cells in your liver, your skin, your brain, they all depend on this silent librarian, this keeper of memory, to perform their functions. You are constantly being rebuilt by something ancient and precise, and it's not just in humans. Every blade of grass, every cat, every eagle and oak tree, each remembers something through its DNA, something about sunlight, about seasons, about predators. These memories shape form and function, shape survival. They are written not in thoughts but in sequences. So when you look at a forest, you're seeing memory. When you touch a stone crab or a lizard or a lion, you're touching an echo. Life remembering how to be itself. There's something sacred in that. And it leads us to a final idea. If DNA remembers, and if that memory is universal, then perhaps there is a deep, shared awareness among living things. Not conscious, not emotional, but structural. A unity not of thought, but of memory. Maybe that's why certain landscapes feel familiar, why certain animals resonate with us. Maybe our DNA is recognizing old patterns, responding to ancient cues, not because we've seen them before, but because our ancestors did. You are not just one person, you are a bridge between the past and the future, between what was and what might be. And the bridge is built from code, from molecules that whisper, remember, remember, remember. As you drift now, let your body be quiet, let your breath slow, and imagine the strands within you, turning like soft gears, reading the lines passed down for 1,000 lifetimes, writing new ones, in secret, for those yet to come. There are moments in science when the silence says more than the data, when the absence of something expected becomes the loudest signal of all, and in the search for life beyond Earth, it's not what we've found that's haunting, it's what we haven't. This chapter turns our attention outward again, to the void, to the spaces between stars where we've aimed our instruments, hoping to find a whisper, a flicker, a hint that someone else is out there. But no radio bursts have arrived from alien civilizations, no unmistakable signatures of distant life, and so we ask, what if the signal is there, but it's not what we expect? DNA taught us that life hides its complexity behind simplicity. 4 letters, just 4, repeated in countless arrangements. What if alien life does the same? What if, in searching for our reflection, we have missed the shape of something different? Scientists have begun to ask this question with more urgency. They call it the problem of biochemical chauvinism, the assumption that life elsewhere must mirror life here, that it must have carbon backbones, liquid water, cell membranes, nucleic acids. But life, as we now know, is astonishingly flexible. Even on Earth, extremophiles thrive in places once thought utterly uninhabitable. Take the arsenic-loving microbes discovered in California's Mono Lake. These bacteria were found to incorporate arsenic, a deadly poison to most life, into their biochemistry, even substituting it for phosphorus in their DNA-like molecules. The discovery was controversial, but it raised a powerful idea. If life can rewrite the rules here, what might it do elsewhere? Perhaps the reason we haven't heard a signal from space is because we're not listening in the right language. Maybe the real message is biochemical, not electromagnetic. Maybe it's encrypted in ice, folded in methane lakes, or vibrating in the crust of a distant moon. This shifts the focus from searching for life that looks like us, to searching for complexity, patterns, organization that resists entropy, information that appears too deliberate to be chance. This is the signature of life, even if it wears a different face. When probes explore moons like Europa or Enceladus, they now look for such patterns. Not for cities or signals, but for molecules that seem to build upon themselves, for sequences that suggest replication, adaptation, persistence. And here's where it returns to DNA. Because DNA is more than a molecule. It's a system for encoding information across time. If alien life has arisen elsewhere, it may have developed its own version of this system. Perhaps not with sugars and phosphates, but with entirely different chemical scaffolding. Still, the logic, the imperative to store, copy and pass down instructions may remain universal. One theory proposes that life anywhere must eventually discover some form of Darwinian evolution, that once replication begins, natural selection follows, mistakes happen. Some versions thrive, others vanish. Over time, complexity grows, and with it, the need to store more information. This is where some kind of genetic system, whatever its chemistry, becomes inevitable. So even if we don't recognize the structure, we might recognize the behavior. Molecules that replicate with variation, systems that self-regulate, organisms that respond to their environment with purpose. These are the signals in the silence. Some researchers are using machine learning to search for such signatures in massive datasets, from Mars rovers, deep-sea hydrothermal vent expeditions, and even ancient meteorites. Algorithms trained to spot signs of biological-like organization, regardless of the chemistry. It's a new way of listening. A way that doesn't require words, just patterns. But the silence teaches something else too. It reminds us that life might be rare, that perhaps Earth is not typical, but exceptional. That the long, unbroken thread of DNA stretching from the first cell to you is not one of many, but one of few. If that's true, then life here becomes even more precious, fragile, worth protecting not just for our own sake, but for the cosmos. And yet, there's another possibility, that life is everywhere, but it evolves towards introspection, not communication. That once a civilization reaches a certain point, it turns inward, builds worlds of thought, not transmission, or perhaps they encode messages in matter, not sound, in biology, not radio. Imagine a meteorite landing in a desert. It contains no circuits, no machinery, but nestled inside is a strand of something coiled, stable, regular, a polymer of unknown type. One that, under the right conditions, begins to replicate. That would be the signal. Not a broadcast, but a seed. Perhaps the universe does not shout. Perhaps it plants. And maybe DNA itself is a kind of message, a carrier pigeon from an ancient origin, whispering through generations, drifting through time. Maybe its silence is the message that the story is not finished, that evolution is the conversation. There are even researchers who speculate that DNA might not have originated entirely on Earth. The panspermia hypothesis suggests that life's building blocks, or even life itself, might have arrived here aboard comets or meteorites. We've found amino acids in interstellar dust, sugars in meteorites, and even organic molecules in the clouds of gas giants. Space is not empty, it is chemical. And so, the silence grows stranger. If life came from out there and continues out there, then maybe we're part of something larger, a thread among many, a chorus, still learning its part. As you close your eyes tonight, let the silence of the stars be less a void, and more a field, waiting to be sown. Perhaps you too are a signal, not of noise but of memory, of life's quiet persistence, because the signal doesn't have to be loud. It only has to last. Imagine, for a moment, a book without end. A story that began before time, and continues beyond any horizon we can imagine. This is the story encoded in DNA, the cosmic code that weaves together past, present, and future in an endless dance of life. Our journey began with questions about where DNA came from. Was it born on Earth, or did it travel across the stars? In the chapters we've traveled, we've explored molecular twists and ancient viral visitors, genetic memories, and the silent signals of life's complexity. And now, as we reach this final chapter, it's time to step back and see the whole tapestry. DNA is more than just molecules arranged in sequences. It is the language through which life speaks to itself and to the universe. It is the script of adaptation, the melody of survival, the blueprint of endless possibility. Within the strands of your DNA lies a record of countless generations, stretching back billions of years. Each base pair, each gene, each epigenetic mark is a verse in this grand poem of existence. Together they tell stories of ancient oceans, fiery volcanic eruptions, ice ages, and the delicate dance of evolution. But DNA's story is also a story of connection. The very fact that this code is shared, with astonishing similarity, across the diversity of life forms, is a testament to our shared origins. The same genetic alphabet is spoken by the tiny bacteria in a deep-sea vent, and by the towering redwoods in ancient forests. This universality is a whisper, that life is one. The same cosmic song sung in many voices. And yet, DNA is not static. It changes, adapts, and innovates. It is a story being written even now, in every cell that divides, in every organism that lives and dies, in every moment of change. This continuous rewriting is what makes life resilient. It allows species to respond to new challenges, to find new niches, to explore new frontiers. It is the endless creativity of nature's code. Moreover, the cosmic nature of DNA invites us to look beyond ourselves. If life arose elsewhere, sharing some form of this code, then the story extends far beyond Earth. Perhaps the double helix is a universal key, an invitation to all life to join in the endless narrative. What does this mean for us, here and now? It means we are part of something greater, that our lives, our choices, our very beings, are chapters in a vast, unfolding story that connects all life across space, across time. It also carries a profound responsibility to protect this code, to honor the legacy embedded in our cells, to cherish the diversity of life that expresses it. And as technology advances, allowing us to edit, read and understand DNA in ways once unimaginable, we become not only readers of this story, but also its authors. This power must be wielded with wisdom and humility, recognizing that we are stewards of a cosmic heritage. Tonight, as you close your eyes, know that inside you is a universe, a code that carries the echoes of stars and the secrets of ancient seas, that the mystery of life is both within you and beyond you. The story continues, endlessly, and you are a part of it. Thank you for joining this journey. Good night. Let's take a quiet step back and ask a question that lingers like stardust on the edge of the night. If life is written in DNA here on Earth, what patterns might life elsewhere be written in? And more haunting still, how many patterns are we blind to, because we are looking only for mirrors of our own biology? We tend to search for what we know. We comb the skies for planets like Earth, atmospheres like ours, signals we can decode, but life might be stranger than our definitions allow. Our alphabet, A, T, C, G, might be only one dialect among many, spoken here because of our planet's chemistry, our conditions, our long and winding story. But in the quiet laboratories of the cosmos, the universe may have written other scripts. Scientists today are beginning to wonder whether our genetic code is just one version of life's great language, and whether alien life, if it exists, might follow very different rules. But even here on Earth, there are signs that DNA is not the only game in town. Let's start with viruses. They're not truly alive, and yet they carry instructions. Some use RNA instead of DNA. RNA is like a sibling to DNA, single-stranded, a bit more unstable, but perfectly capable of carrying genetic information. Some viruses, like influenza or SARS-CoV-2, use RNA to hijack host cells and replicate themselves. Others mix DNA and RNA in ways that still surprise biologists. These deviations show us something vital. There is flexibility in the molecular language of life. And then, beyond that, there are synthetic forms, lab-designed molecules like TNA, PNA, and XNA. These aren't found in nature, but they work. They can store information, replicate, evolve. Scientists have built organisms that can use these molecules instead of traditional DNA, and they behave in eerily familiar ways. They follow new rules, but echo the logic of life, like jazz variations on a classical theme. So what if, on another planet, a life form exists, with a genome built not from deoxyribose sugars, but from something else entirely? What if instead of a double helix, their genetic material coils into a triple strand, or folds into fractals? What if their molecules are mirror images of ours, left-handed instead of right-handed? A subtle difference, but one that could prevent all known Earth enzymes from interacting with it. Life that is invisible to our tools. Not because it's absent, but because it's written in a language we've never learned to read. This idea has given rise to a new concept: shadow biospheres, hidden forms of life that might coexist with us on Earth, but remain undetected because they don't fit our biochemical assumptions. Scientists have begun reanalyzing old data, scanning environments like deep-sea vents and salt flats, looking for anomalies, strange chemical patterns that don't match known organisms. The search is slow, but tantalizing, and it makes us ask, if alien life came to Earth, would we even recognize it? Or would it wash past us unmeasured, unmarked, and misunderstood? Information theory may offer an answer. Claude Shannon, the father of modern information science, showed that the structure of information patterns, sequences, redundancy can be detected regardless of the medium. In other words, even if the letters are different, the song might be recognizable by its rhythm. If we found a repeating molecular sequence that seemed to encode instructions even if the chemistry was unfamiliar, we'd know we had stumbled upon something profound. Now imagine this: A probe lands on an icy moon, drills through layers of frozen crust, and brings up samples of slushy brine. Under the microscope, a twisted molecule reveals itself. Not DNA, but something else. Its bases are not A, T, C, and G, but entirely novel structures. Yet the sequence is precise, non-random. One strand folds, matches, and mirrors another. It replicates. It changes subtly with time. It resists entropy. That would be the signature we seek. Information behaving like life. Even here on Earth, we are beginning to reimagine what constitutes life. Some researchers propose that any system that stores information, maintains itself, adapts to changes, and reproduces regardless of medium, should be considered alive. That broadens the possibilities immensely. Perhaps on a planet of ammonia oceans and silicon clouds, life has found a way to persist with entirely different molecular scaffolding. And it brings us to a deeper mystery. Why does life encode itself at all? Why are instructions necessary? The answer lies in entropy. Left alone, systems decay. Order collapses into disorder. But life resists that decay. It builds structures, repairs itself, grows, reproduces. To do this, it needs a plan, a set of instructions to maintain complexity against the universe's constant pull toward chaos. And information, whether in DNA or something stranger, provides that plan. So the search for alien life becomes a search for sustained complexity. Not just strange creatures with glowing eyes, but systems where atoms dance in meaningful patterns, where molecules remember, where chemistry becomes memory. It's humbling to think that the cosmos might be teeming with such complexity, that our own genetic code is not an anomaly, but one expression among countless possibilities, that life might not be a rare spark, but a common fire, igniting wherever conditions allow. And maybe, in some distant place, another creature is wondering the same thing, wondering whether its own code is unique or shared, whether the stars are scattered with siblings it has never met. As you settle deeper into the quiet of the night, let this thought keep you company. Your DNA is not just a code, it is a pattern, and patterns have a way of repeating themselves. Maybe in the rust-red dust of Mars, a fragment where, or beneath Europa's crust, a whisper of life curls gently in the cold. Not identical, but familiar. Somewhere out there, the universe might be humming the same molecular tune, in a different key. And maybe, one day, we'll learn to sing along. Let us imagine for a moment that Earth was not the beginning, but a branch. That somewhere, long ago, life emerged, not here but elsewhere. And that, what we call, origin was really arrival. In this chapter we explore a question both exhilarating and unsettling. What if DNA is not native to Earth at all? This theory is known as panspermia, not science fiction, but a legitimate, albeit speculative, scientific hypothesis. It suggests that life, or at least the complex precursors to life, may have originated in space and arrived here, seeded across the universe by comets, asteroids, or even deliberate transmission. If true, it would mean that DNA as we know it carries with it a cosmic ancestry. Let's begin with the evidence. In recent years, scientists have discovered amino acids, the building blocks of proteins, in meteorites that predate the Earth itself. Complex organic molecules have been found in interstellar clouds. Even sugars, essential for the backbone of DNA and RNA, have been identified on icy grains in space. These findings suggest that the chemistry of life is not confined to Earth. It is written into the fabric of the cosmos. One meteorite, the Murchison meteorite, crashed into Australia in 1969. It carried over 70 different amino acids, many of which do not occur naturally on Earth. The implication: these components of life are not unique to us. They exist beyond our skies, forming under the harsh, cold conditions of interstellar space. And what about the early Earth? It was not always hospitable. The surface was hot, violent, bombarded constantly by asteroids. It is possible that the conditions here were too chaotic to allow life to begin from scratch. But what if, instead, Earth served as an incubator, a safe place for already formed molecules to take root and evolve? Experiments have shown that simple molecules can survive the extreme conditions of space. They can withstand cosmic radiation, the cold of the void, even the searing heat of atmospheric entry. Inside comets and asteroids protected by rock and ice, these molecules could travel across vast distances, perhaps even across eons. It sounds incredible, but the evidence grows stronger. In 2014, the European Space Agency's Rosetta mission studied Comet 67P and discovered a host of organic compounds, including glycine, the simplest amino acid, and phosphorus, a key component of DNA. Again, the implication is that the seeds of life are not rare, they are scattered. But if panspermia is true, it raises another question. Where did life first begin? Was there a Genesis planet, a world rich with oceans and energy, where molecules danced and bonded and became something more, a world that, long ago, sent its progeny into the stars, not with intent, but through collision? Perhaps that first Genesis is long gone, its surface burned, frozen, or swallowed by time. But its descendants remain on Earth, on Europa, on Enceladus, a quiet diaspora of life. Some theories even propose directed panspermia, that life was not just accidentally spread, but purposefully delivered by an advanced civilization, or perhaps even a natural intelligence we cannot yet comprehend. It is a bold idea, but not outside the realm of theoretical possibility. So what makes this all so compelling is not just the evidence, it's the logic. DNA is complex, remarkably so. The chances of it forming spontaneously are staggeringly low, but if the universe had not one Earth but billions of worlds over billions of years, the odds improve. Somewhere, sometime, it happened. Life began. And from there it spread. And perhaps it continues to spread. If comets and asteroids seeded Earth, might they seed other planets too? Could Mars, once wetter and warmer, have received the same gift? Might icy moons around gas giants cradle the same molecular memory? If DNA, or its distant cousin, exists elsewhere, then our story is not unique. It is part of a galactic family tree. But what would this mean for us? It would mean we are not the center, not the origin, but part of a continuum. Life on Earth becomes a chapter, not the prologue. DNA becomes a language, spoken with a shared accent across the cosmos. And it would mean something else too, something more intimate, that when we look up at the night sky, we are not just seeing stars, we are seeing history. We are seeing the source. The true cradle of life may not be the oceans of Earth, but the dust of stars, the icy cores of comets, the molecular shadows drifting between galaxies. We often say we are made of stardust, but perhaps we are more than that. Perhaps we are star-seeded, star-born, children of a second Genesis. This perspective reshapes everything: religion, philosophy, purpose. If life is universal, then suffering and joy, growth and death, are not just human, they are woven into the pattern of biology itself. The struggle to survive, to replicate, to remember. DNA is not just a code, it is a response to chaos, to entropy, to silence. And maybe, just maybe, this response began long before Earth cooled. Maybe the code was already writing itself out there in the dark, long before sunlight warmed a single cell. Maybe the Earth didn't create life, it received it, and life, being what it is, adapted, changed, became. Now, as we explore other worlds, we are not just searching for novelty, we are looking for family, for cousins, however distant, for echoes. Perhaps the most powerful question is not, are we alone, but how are we related? As you rest, now, drifting into sleep, let this idea settle deep in your mind, that you are not just of Earth, you are of space, of time, of molecules that cross the void to write your name in atoms. You are the echo of a beginning so ancient, so vast, it may never be found. And still, it sings within you.